Hello everyone. In this class, we'll be discussing about the concept of stress. And one thing which you should notice is that the way we develop our theory of stress, meaning what stress is completely independent of the way we developed our theory for strain. So they are two sort of different species altogether. Yes, they will have a relationship when we consider linear elasticity, so-called the Hooke's law, which you may be aware. But the development of its theory and the understanding, meaning what stress is and what strain is completely independent of each other. So I hope you will keep that in mind, and let's now sort of begin what happens. So what we did in the previous discussion was that when you say have a solid body and under suitable approximations which we had specified, there were deformations and you wanted to quantify those deformations. Okay, and strain and rotation were two tensors which we are yet to define what a tensor is something which we had defined as a quantification of what those deformations were. Now we want to see how the forces are transmitted through an elastic body, in the sense that every point, what is the force and how they are transmitted across, say, when you apply a loading at the boundary of a solid. So this will lead us to certain new terms which you may or may not be aware before, or you may have heard of them before, but perhaps not in this way. So let's go with these things and see what happens. All in all, we'll be only considering so-called static cases in which all the points are in equilibrium. There is no acceleration anywhere. However, if you ever move to a problem in, say, dynamic, then you will have to consider those accelerating terms. So I'll point out where they occur, but definitely not keep that in mind. One of the things which you should know and note, that whatever we discuss in this topic of stress, it does not require your material to be linear elastic. Okay, it can apply to any type of material, non-linear elasticity or whatever, viscoelasticity, plasticity, whatever it may be. So the concept of stress is universal. Only when you try to relate it to strain, at that point in this course we'll see what those assumptions are about the material. So let's see what happens. So if you have a solid structure, and you must be by this time knowing the difference between an ideal solid and an ideal fluid. An ideal solid is able to sustain a shear uh, deformation or a shear loading, but ideal fluid is not able to sustain. I mean, an ideal fluid will collapse if a shear force is applied on it. A solid will not. So that's the difference between an ideal fluid and an ideal solid. So I hope that's clear, and perhaps you knew this already. So when you have a solid in which you apply certain external forces, then there are internal forces which are induced inside the body. Meaning you have a solid like this, and then you apply these forces externally, you as an external agent, but there will be these forces which are induced internally. You didn't apply these internal forces, but they are induced as a result of this. You're applying the forces outside the body, on the boundary. Now, one of the basic assumptions of continuum mechanics, which we followed in the last discussion on strain as well, was that they are continuously distributed within the solid, meaning all the points in this solid will have some sort of a force, may or may not be zero, we don't know that, but there's a continuous distribution, in the sense you cannot say that you have to jump from this point to this point. So just like you had the strain which was defined at all points inside a solid body, similarly you will have the stress, which we will see now, defined inside the solid body. So these forces is what we want to use the term now. So let's just call the word forces, so called the internal forces. Okay, and they are distributed. continuously throughout. So this is an assumption of a continuum mechanics. If this was not a continuum system, in the sense if it was a system which was made up of molecules or atoms, a so-called discrete system, then this treatment would not hold, this continuity would not hold, and hence many of the things which we discuss will not be true. Of course, there are ways which we get around in, say, molecular dynamics and how to define the stress and strain, but this, what we are discussing now, is only for continuous solids, not for atomic systems. You may also at this time wonder, why am I talking about discrete systems and continuum system when everything in this world is made up of molecules? It's about how you see. For example, if you have a piece of block in front of you, I mean, it may be your mobile phone, for example, and if you, there are two ways to see this. One is to see it from your naked eye. So E is your eye. So in this one, you will have a so-called macroscopic view of it. Okay, and this will look a continuum solid. The other way is, say, if you had a very powerful microscope, you will see not a continuous solid but a collection of atoms which may or may not be arranged in a well-defined manner. Okay, so this is a so-called atomistic view. So this is discrete. So continuum mechanics, or the concept of continuous solid, is the way you look at it, and the way you look at it, you develop your theories accordingly. If you were looking at your mobile phone as a collection of atoms, you would have to move to, say, molecular dynamics and then try to see what strains and stresses would mean over there. So right now we are looking at everything from a macroscopic perspective. Okay, so let's define some of the forces. So these internal forces which we have to define the forces into two categories. One of them, say, is the body force. Okay, so they are clearly proportional to the mass of the body. You may be aware that gravity is a body force, so you know that it's clearly proportional to the mass. F is equal to mg. And this is reacted with an agent outside of the body. So gravity is definitely one case. So this is proportional to mass, and it is reacted, as your author says, with an agent outside of the body. Okay. Now, if you look at one example which I have for you, it was from your textbook. You have this cantilever beam. Let me just. Okay, and obviously it has its forces. So I am showing the body forces, which is F. Okay, both of them are vector, both F and the position, for an arbitrary origin, and your beam should deform something like this. Okay, under the weight, under its own weight, it should deform something like this. Okay, so it has a so-called self weight loading. Okay, so some of the examples, as you know, are gravitational field, magnetic forces, and so on. Okay, now if you use the concept of continuum mechanics, what is the concept of continuum mechanics? That this force will be continuously present throughout this solid body. Okay, so at every point of this continuous solid, you will have a certain force defined. Okay, so it cannot say that we don't define the force at this point. That cannot happen over here. Okay, now we use another term over here. It's called a body force density. And that is called, actually the term F which I have written over here was actually the body force density, but I'll just define it yet again. It's defined such that the total resultant body force of an entire solid can be written as a volume integral. What it means is that the total resultant force over the entire body is something like this. Okay, meaning that if you have a body force density F of x acting at this point and a very small volume around it is dV, okay, now you integrate this entire F dV for this entire solid over the entire volume, you will find the resultant force of this. Okay, so that is how this body force density is defined. And as you know, like your weight is something like this, so you can, your total weight can be something like this, which is Fr. Okay, the resultant of all these small body force densities acting over little volumes. Okay, now that was about the body forces, which was so called our classification of forces of the first type. Then we have the other force, which is called the surface forces. How are they defined? I mean, one of the first thing, as the name says, that it always acts on a surface, okay, and result from physical contact with another body. Okay, so for example, if you try to press the pen or your pencil with your fingers right now, there are surface forces generated. They are clearly generated on the surface, both of your pen and your fingers, and they are a result because of the physical contact with your finger and the pen. Okay, so there are electrostatic origins of these forces, and you can always classify them as normal forces or sort of shear or friction forces, but this is what the surface forces are defined. Now, just like we understood it, the body forces, let's look at this. If you have a part of a beam, okay, which is okay, you apply a force like this. Now, it is not necessary that the surface forces have to act only on the outer surface. You can create fictional internal surfaces and then define the surface forces. For example, in this beam which is there, or a bar for example, okay, which you have over here, you apply forces like this on the edges, which is fine, and then you can define them to be surface forces. But what you can also do is create a artificial surface like this, okay, with this purple ink which you see. In this case, now your now at this surface you will have these surface force density. which is defined as Tn of x. Okay, and let me just define what the surface force density is, and it's on this inclined surface which you have created through this, and obviously there will be a corresponding other half which will have so-called equal and opposite forces because of the third law of motion. So one of the points which you should note that S is a virtual surface. Okay, meaning this is not a real cut, physical cut which you have made. You have imagined that if there was a cut like this, then the forces would be on this surface would look like this. Okay, why is it done? Because we want to investigate how are the internal forces internally in a body. Okay, I mean, what is the surface forces inside a solid body? So we have to virtually make this cut. Okay, because body forces itself cannot help us in understanding what we are doing over here. Okay, so the surface force density Tn of x is defined as Fs in the very same manner. So the surface force density is actually Tn of x ds. Okay. How is it defined? The resultant force over the entire surface S can be expressed as the integral of a surface force density function. We call it a function because it is changing with the position x. Okay, so Tn of x is the surface force density function. Now let's try to see what these things are. One of the difference between, say, the surface force density and the body force density is that you have this n over here. Okay, this, remember, was not there over here. Okay, there was no n, but here you have this n over here. Now what this n means, it is the orientation of virtual surface. Meaning, say if you have something like this, you could have created a virtual cut like this. In this case, n would be in this direction. You could have also, for the same point of interest, say this was your point of interest, you would have created a virtual cut like this. In this case, it would be like this, and so on. So there are infinite possibilities of how that virtual surface is created inside a solid at a particular point of interest, which is this one. Okay, so that's why you have to specify what that n is, since there are infinite possibilities. So you have to be specific. The surface force density at this point, okay, at this point is given by this, where the orientation is this. Okay, and clearly if that point is this, then the surface would be, the small surface area ds would be something like this, and so on. Okay, so the same arguments apply as they were in the previous case. Since the body forces and the surface forces and the body forces and the surface force densities have been defined, let's now move on and see what is next in store for us. Okay, so the next concept which we would want to learn is about the traction vector and stress tensor. So let's do that. Okay, just like the strains were used to quantify the deformation internal to a solid, we want to define some other terms to quantify the nature of internal forces and how they are distributed within a solid. Okay, now for this, just like for deformation, people knew what that deformation, but to quantify ki how much is the deformation, you required a quantity called strain, so that in different directions you could tell this is the strain and so on. Similarly, to quantify the forces, the distribution of forces inside a solid, you will need to define what the stress tensor is. So that's the motivation why we are trying to learn, because it's not as simple as just a vector giving a magnitude and a direction. Okay. Okay. So let's see. You have this externally loaded body. Okay. You have this P3 force. You have a P2 force. You have say a P1 force, and then there are these distributed loading as well, P. Okay, now we want to investigate the internal forces, say at this point, okay, which is internal to the solid. Of course, because it's a continuous solid, so whatever we are discussing will be true for any point which is internal to this solid. So what we do is we want to create a section by having a virtual cut, something like this, cutting across this. Okay, so this is the virtual cut which has happened, and this was a point of interest. After this virtual cut, our solid should, pardon my bad drawing and writing and speaking, but I hope all of it is making sense. Okay. Okay, so this is the surface which we have created. This is a section body. Again, it's a virtual cut, so it's not that in reality we have cut this solid into two parts. The point of interest, this point, is again say right smack in the center of it, and let's say that it has an area delta A, a finite area delta A. The orientation is n. Okay, the outward normal vector is something like this, and we have the surface force which is acting is delta F. Okay. So delta A is a small area with a unit normal vector n. Now the resultant surface force which is acting is defined by delta F. Very clearly notice what I have shown as a scalar and what I have shown as a vector. There is an overhead sign everywhere for a vector. Okay. Now we define something called the traction vector is equal to, traction vector Tn of x is equal to limit of delta A tends to 0 delta F by delta A. So this is defined, hence I am putting this equality over it. Okay, this is not something which we have derived. We are defining that the traction vector is this. Now, one of the important things which you should note is how we have used the so-called surface force density concept into defining what the traction vector is. Okay, so very clearly see the difference, how we have migrated from say here to here. Okay. Okay. Obviously, as you can see, the traction vector depends on both the spatial location and the unit normal vector to the surface concerned. Okay. So that's where this idea comes in, that even though you may be investigating the same point, this point, remember, okay, there is a possibility of having infinite traction vectors because there are infinite orientations possible for this virtual plane which you have created. Okay, so this is always defined with respect to a certain normal. Okay. Okay, so it's also a function of the orientation or the normal. Now, it's very easy to agree that this is, say, the left half. This half of the solid is over here. We have not drawn the other half of it, which looks, say, something like this. Okay, but if you had, and the same point, this is the point, this is the point over here, and the same point will lie over here as well, because this point is shared between these two halves. Okay, by the third law of motion, you can write that the traction vector on this one is minus of the traction vector of minus n. Okay, because this orientation will be minus n at the same point. See, the point is same in both the cases. Okay, x is not changing, but minus n and n will be there because the outward normal is in the opposite direction. So by the third law of motion, this is the this is what we have arrived at, and it's a fairly useful thing to know for a traction vector. Of course, you knew it for forces, but to know this for traction vector, especially since you have just defined what a traction vector is over here, is good thing to have. Now let's consider a special case, or at least three special cases. Okay, so delta A is coinciding with the three coordinate planes, sorry, with the unit normal vector pointing along the positive. So let me explain what this statement means. See this delta A over here, where did it go? Over here. Okay. Now let this delta A, the small area delta A, be such that in one case the outward normal, which is n, is equal to I cap. Okay. In the other case, let this delta A be such that this outward normal is equal to j cap. And in the third case, or it's also called E1 hat, this is called E2 hat, and in the third case you can have this delta A which is oriented such that n is equal to E3 hat. So this is the meaning of these three special cases. This delta A is coinciding with the three coordinate planes. So in the first case, this one, which plane would this be? This would be the YZ plane. Okay. In this case, what would be the plane be? It would be the xz plane. And in this case, what would be the plane be? Delta A would coincide with the xy plane. Okay. So these are the three possibilities, three special cases. How many else cases remain? We are still left out with infinity minus 3 cases. Okay. But we'll worry about it later on. Let's just write only for these three special cases. So one of the other things about a vector, because traction is a vector, is that it can be written in terms of the basis vectors of the space. I will just give you an example. So if this is, say, the I and I cap and j cap direction, okay, and you have any vector, say the position vector, it can be written like, say, 2i plus 3j, okay, cap, and maybe it has a unit, meters, centimeters, whatever. Say you want to write the velocity, it can still be written as 4i plus maybe 0j, okay, and meter per second. You want to write the acceleration, it can be written, say, 2i plus 19.6 j plus, in a three-dimensional case, you can of course write it as say 20 k cap, meter per second square, and so on. Any vector can be written in terms of I, j and k in a three-dimensional case, and these quantities which you see 2, 3, 4, 0, 2, 19.6, 20, they are all scalars. Okay, you knew this, but I am just trying to bring that point to you directly. So it's like defining a vector using the basis vectors of the space. The basis vectors of the space are I, j and k, because you can define any vector in this space using these three basis vectors. Okay, so by the same logic, the traction vector for the first special case Tn x n is equal to E1 hat can be written as E1 hat plus E2 hat plus E3 hat. Okay, I have to put up some scalar numbers over here, but this form is exactly same. Similarly, the traction vector for the second special case, what is the plane for which delta A is coinciding for this one? I have just discussed. Please look it up. Okay, this is E1 hat. I'm just removing this. All the gaps can have a scalar quantity. And similarly, the traction vector can be, for this third special case, can be written as okay. Now E1, E2, E3 are the unit vectors along each coordinate direction. So E1 hat is I cap, E2 hat is j cap, E3 hat is k cap. Okay. Now what I do is very innocently and as if I don't know anything about stresses, and which at this point perhaps you don't either, the way we are developing this theory, I want to put a scalar quantity over here. Let me just call that as sigma xx. Okay, sigma x. Let me just call it tau xy. Let me just call it as tau xz. Over here, let me put up another quantity, tau yx, sigma y, tau yz. Here, let me put the scalar quantity tau zx, tau zy, and sigma z. Now, you can always question, why am I doing this? Well, I could have written A, B, C, D, E, F, and so on, or A1, B1, A2, B2, whatever else. You wouldn't have questioned then. So you should not question now as well. Okay, it's just a scalar number as of now. It does not mean anything at this stage. Okay, so in fact, I'm in defining what this is right now. The 9 quantities sigma x, sigma y, sigma z, tau xy, tau yx, tau yz, tau zy, tau zx, tau xz are the scalar components of the traction vector on each of three coordinate planes. Okay, so these quantities are the scalar components of the traction vector at this point. Now is where I introduce them. These 9 components are called stress components. Okay, so sigma x, sigma y, sigma z are the so-called normal stresses, and tau xy, tau yx, and the other are called the shear stresses. Okay, now if you want to write them in a matrix form, you would have to say write something like this. I want to write these 3 equations in a matrix form. Let me just show that to you. Sorry, I want to write them as this system of linear equations. I want to write it like this. So it will be sigma x, tau xy, tau xz, tau yx, sigma y, tau yz, tau zx, tau zy, sigma z, and this would be e1 hat, e2 hat, e3 hat. Okay, so this matrix form is just like writing this 3 system of linear equations. Okay, sorry. So this particular matrix which you see is obviously the stress tensor, where sigma 1 1 would be equal to sigma x, sigma 3 2 would be equal to tau zy, and so on. Okay, for I comma j going from 1 to 3. So again, it's a matrix form and not necessarily a tensor, but it will be a tensor because it will show certain properties which we are to define in our very next discussion. Okay, so it is a second order tensor and obeys certain transformation laws. That's why it's a tensor, and you may already be aware of how they are defined. So if you have the x, y and z axis defined in this form, and if you have conveniently drawn, so remember what the delta a was in the first case. It was along the normal was along the x direction, so this is the first line, sigma x, tau xy, and tau xz. The second line for the xz plane, that would be sigma y, tau yx, and tau yz. And the third one will be on this face, so this would be sigma z, tau zy, and tau zx. So you perhaps clearly knew this, but this is a good time to revise if for some reason you had forgotten about it. Okay, now the positive directions are clearly shown in this figure which we have just drawn, and basically tau xz is the stress on the x plane, because this plane which you see is x equal to something, so it's stress on the x plane in the z direction. Similarly, look at tau zx, it is a stress on the z plane because this plane is z equal to something according to this coordinate, z equal to 2, z equal to 3, we don't know, and in the x direction, on the z plane in the x direction. So that's an easy way to remember how the shear forces, shear stresses are. Okay, now that's already given to you, and let me now come back to what we had done. We had defined the traction vector, and then we had said that certain special cases were taken. In fact, three special cases were taken where the area was supposed to be aligned along the three coordinate planes, and hence the directions outward normal was coinciding with the x, y, and z axis. Okay, now you have to now consider about the so-called remaining infinity minus 3 cases. And how do we do that? We do it by having a oblique plane. I'll draw that. So you have the x, you have the y, and you have the z. So the oblique plane is something like this. Okay, so this plane is an oblique plane and it is not aligned to any coordinate plane, and hence the outward normal of this oblique plane will not be just say E1, E2 or E3, it will be a combination of them. So let me just draw that n over here. So n, which is the outward normal, can be written as nx E1 hat plus n2 ny E2 hat plus nz E3 hat. Okay, so this is the unit normal to the surface, and this is obviously an arbitrary orientation. This is those infinity minus 3 cases. Okay, special 3 cases are done. This is the infinity minus 3 cases. So the outward normal is this, so the unit normal to the surface. The surface is shown by this purple ink in front of you. Now, what are nx, ny, and nz? These are the direction cosines of the unit vector relative to the coordinate system. So let's sort of go back and see what direction cosines are. Okay, since they are extremely important in how we deal with this. So nx, ny, nz are direction cosines with respect to x, y, and z axis, meaning nx is the cosine of the angle between n and x, or I cap. Ny is the cosine of the angle between n, the vector n, and j cap, and nz is the cosine of the angle n and k cap. Okay, so that's how we define what the direction cosines are. Now let's do something over here. Let's call this point as A, this point as O, this as B, and this as C. Let's call the coordinates of this as A0, 0, 0, B0, and 0, 0, C according to this coordinate system. Okay, so I hope you'll agree that there's nothing, and O is obviously the origin, which is 0, 0, 0. What I'll do now is do a force balance. Remember, what is happening is that you had a certain point in a solid, okay, and that point now is O. You have drawn your coordinate system x, y, and z, and then you drew this so-called plane that made a tetrahedron. Can you see the tetrahedron over here? It has the plane COA, it has the plane AOB, and it has the plane BOC. So this is a closed part of a small part of this solid body, and what we want to do is we want to say that this pyramid element, which is inside the solid, and at the point of interest. The point of interest never changes. Okay, the point of interest is this, and this, the same one. Then it's also over here, okay, or over here, whichever way you would want to see, in the center of that cube, and the same point of interest is over here. The stress is being defined at a point. Okay, this pyramidal element which is inside the solid and at the point of interest, and clearly the planes of this pyramidal element are oblique to the coordinate axis. You want to say that it is in equilibrium, meaning this pyramidal element is not accelerating. So when will it not accelerate? When all the forces are balanced. Okay, so let's try to write out all the forces and see how we can say that. So the traction vector, okay, is Tn. So first let's draw, there are four planes, so let's consider the ABC plane. So Tn for say n is multiplied by the area. What is the area? Triangle ABC. So these two things combinedly give you the force. Remember, when you do a force balance or a so-called an equilibrium balance, you can only equate the forces or the moments. Okay, moments is when there is no angular acceleration, and force is when there is no translational acceleration. You do not ever balance the stresses or tractions, you can only balance the forces. So this is the forces, and then let's write out for Tn, n equal to E1. Okay, this plane A, so triangle, sorry. So this is the first force which we have written, triangle ABC. Now let's look at this triangle, this plane BOC, triangle BOC. What are the traction vector on this? Obviously n, but n in this case will be equal to minus of E1 hat. Reason is that the outward normal will be like this for this plane. So that's why you have a minus. Similarly, you will have a minus E2. That would be multiplied by triangle. Let me just use another line. Okay, so we are now referring to this plane COA. Okay, so the outward normal is in the minus E2 direction, and the area is triangle COA, and then the last one would be N minus E3, and this would be multiplied by the area triangle BOA, and this all has to be equal to 0. Okay, now, and it is to be 0 because you have balanced the forces, since this pyramidal element was not accelerating. Okay, so it was in equilibrium. Now you should remember, a few minutes ago we have said that this can be written as with a minus sign. Okay, similarly this can be written as minus of t of n. Similarly this can be written as minus of tn. Okay, so if you want to simplify this equation, you would write t of n triangle ABC is equal to t n is equal to E1 triangle BOC plus okay. So I hope you can agree to what we have just done. Now this would also imply, since triangle ABC, meaning the area of triangle ABC is not equal to 0. Okay, you can see from this figure that the area of triangle ABC is not equal to 0. You can divide the area on both sides of this, and this would give you, this argument is very important, that you are dividing both sides because this quantity is not 0. If this quantity was in fact 0, then this couldn't have been done. Triangle ABC plus Tn triangle COA triangle ABC, and the last one okay. So this is what we have until now. Now the authors of your textbook have written, from say this we can write the following. Let me just point out. They say that you can write this as n is equal to t n equal to 1 triangle, sorry, this should be in x n y plus t n equal to e3 n z. Okay, so this is what the authors say and this is what we have. So it seems we will be able to agree with the author if for some reason we can write nx as the ratio of these two areas. Okay, and similarly ny can also be written as the ratio of triangle COA, area of triangle COA divided by the area of triangle ABC. So I'm just showing one case, and if I can show one case, it seems it will be convincing enough. Okay, so remember we had done some work over here which I think I'll have to draw again. So this was I cap, J cap, K cap, and the oblique plane was something like this. Sorry, I'll just, I mean, there are ways of saying that, well, this is a projection of that area and hence it should be a cos theta and so on. But I'll show you a more rigorous way to do it, just because was never convincing to me. For a three-dimensional situation, I was always not very clear how you can replace this area with that direction cosine. They would draw some sort of a plane and then say that if you drop this, then you will get that area and so on. But for an arbitrary oblique plane, I could not visualize, and hence you are being made to see the more concrete method to do this. If for some reason you are yourself able to visualize how these two triangles are actually equal to nx, which is the cosine of the angle between n and I, then remember what this was. This was the cosine of the angle between n and I hat. Then it's fine, but I cannot, and hence you are seeing this. Okay, so this point A was, remember, A comma 0 comma 0. This point B was 0 comma B comma 0, and this point C was 0 comma 0 comma C, and this is the origin, obviously. Okay, so let's first of all try to write what is the triangle BOC. Okay, so we are putting a question mark over here, okay, since we don't know whether this is equal to or not. We are trying to check that. So the triangle BOC is easy to write. That should be half into base into height. So the base of triangle BOC is half into C into B. Okay, so that's an area. Now triangle ABC can be written as half into, say, this vector cross with this vector. Okay, so if you do a BC cross BA, if you don't have this factor of half, then it would be the area of the parallelogram. But since you are looking for the area of the triangle, this is true. So let's see how, and I put a modulus sign because we don't want to get some negative numbers over here. So let's see, the vector BC is what? So it's 0 minus 0 I cap plus 0 minus B J cap plus C minus 0 K cap. Okay, this is crossed with vector BA. It is A minus 0 I cap plus 0 minus B J cap plus 0 minus 0 K cap. Okay, so let's see what this should be. I, J, K. Okay, so this is 0, this is minus B, this is C, this is A, this is minus B, and this is 0. Okay, so this should be written as half into modulus of I cap into 0 minus of minus BC, that would be PC. Then you would have j cap, sorry, it would be minus j cap, I'm sorry. This would be 0 minus ca plus k cap, that would be 0 minus ab, so that would be ab. Okay, so this can be written as half into under root. So the modulus of this vector can be written as bc square plus ac square plus ab square. Okay, so this is the first thing which we can get. So BOC, the two areas we have got, and now we have to somehow show that this is equal to nx. Okay, so first let's write down this is what the right hand, let me call this as m and this as p, just because there are too many n's, so I don't want to use an n. So m has been shown to be equal to CB divided by AB whole square plus BC whole square plus AC whole square. Okay, now let's try to write what P is. P is the cosine of the angle between N and I. So this would be, say, a dot product. What was N, if you remember? Nx I cap plus Ny j cap plus Nz k cap. Okay, dot with I. So this would be equal to nx. Okay, so if this has been shown equal to this and this is equal to this, then I think it is fair enough to write this. If you are still not convinced by the angle between n and I mean, you should be, because the numbers are already speaking. But if this is still not the case, you can always do a more rigorous calculation and see how the numbers are playing up. Okay, so this I think should convince you that the nx will actually be equal to this value. But let me think of one last missing. So you have shown that this is true, you have shown the value of this, but actually we have not yet completed. We are still to prove that nx is actually equal to this. So how do you intend to do that? Let's see what nx should be. Nx should be the cosine of the angle between this n which was over here and I. So let me just say that this vector n can be written as the cross product. N is the the unit, let me say, unit vector given by what? BC cross BA. Okay, because this n will be outward normal to this plane, and hence it should be this cross product, the unit vector along this. So lucky for us, BC cross BA has been done, and that value is cross BA is equal to I into BC plus J into AC plus K cap into AB. Okay, the unit vector of this, because directions are always unit vector, will be equal to n, that would be it would be BC whole square, sorry, the unit vector n would be equal to bc by n will be equal to bc by ab square plus bc square plus ac square I hat plus ac by ab square plus bc square plus ac square j hat plus ab by ab square plus bc square plus ac square k hat. And hence this is what nx should be, this is what ny should be, and this is what nz should be. So now we have shown that nx is actually equal to bc by ab whole square plus bc whole square plus ac whole square. Okay, so this has been achieved now, and similarly for ny and nz you can do the same. So I hope this is a more convincing proof than simply telling you that if you project this, you will get an nx or some sort of a cos theta, which I found it hard to visualize. But if you can visualize that, do let me know. Okay, I'll be curious to see. Anyways, so by using this last step, which we had written as nx into Tn okay, we can write, let's see, let's see what Tn n equal to 1 was this term. Tn n equal to 1 was this one. Okay, similarly Tn n equal to 2 was this, and so on. So we'll substitute this over there, this equation, and the other two we'll substitute in what we had written. So let me now go back. So nx has to be multiplied by sigma x e1 hat plus tau xy e2 hat plus tau x3 e3 hat plus ny is what Tn n equal to e2, that would be tau y x e1 hat plus tau sigma y e2 hat plus tau yz tau zx e1 hat plus tau zy e2 hat plus sigma z e3 hat. Now I want to keep the e1s, e2s and e3s together. So let's see, nx sigma x plus ny tau, let me just write it in a different form, sigma x nx plus tau yx ny plus tau zx nz, this is e1 hat plus tau xy nx plus sigma y ny plus tau zy nz is e2 plus tau xz nx plus tau y z ny plus sigma z nz E3 hat. Okay, this was just clubbing E1, E2 and E3s together because that makes us write things somewhat easier. So remember, this is a vector. So T, if I have to write what Ti of or T1 of n would be, not a vector, okay, because Tn is a vector. So T1 of n E1 hat plus T2 of n E2 hat. By the same logic, it's a vector, so it can be written in terms of E1, E2 and E3, where T1n, T2n and T3n are scalars. So T1n is essentially this entire thing, and T2n is by the same logic this entire thing. So in a combined form, I can write that Ti of n is equal to sigma ji nj. Okay. So remember, I mean, if you have a say x over here, you are having an x over here. If you are having a z over here, you are having a z over here. If you are having an x over here, you have an x over here, and so on. So that's why this can be written. The ith component of this traction vector can be written as sigma ji nj. In the expanded form, you can clearly write Ti of n is equal to sigma 1I n 1 plus sigma 2I n2 plus sigma 3I n3. So for I equal to 1, it would be T1 of n equal to sigma 1 1 n1 plus sigma 2 1 n2 plus sigma 3 1 n3. Sigma for I equal to 2, this would be sigma 1 2, sorry, 1 2 n2 n1 plus sigma 2 2 n2 plus sigma 3 2 n3. Okay, so it's just the same thing, where 1 is x and 2 is y and 3 is z and so on. Okay, now this relation which you have just got, this one and this one, they provide a simple and direct method to find forces on an oblique plane, which is the infinity minus 3 cases. So to find the traction vector, okay, on an oblique plane, let me redraw that oblique plane once again for perhaps last time, x, y, z, n, traction vector is n. Okay, so this traction vector can be found out by just this equation. I mean the three vectors. What would you require? You would require n of this oblique plane, okay, like nx, ny, nz, or n1, n2, n3, whichever way you would want to write, and you would require sigma ji for three special cases: sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, 2 2, 2 3, sigma 3 1, 3 2, and 3 3. So if you have these two things, you can find the traction vector for any oblique plane. So for any of the infinity minus 3 cases, you can find, as long as you know the value of the stress vector at that point, and obviously the orientation of this oblique plane. So two things and you have the value. So this is the reason for considering the three special cases. Now just to summarize, if you have a solid body and there's one point of interest, if you know sigma ij, and you know this means that you know the 9 components, okay, you can virtually cut this in any arbitrary orientation, okay, and you will get the traction vector at this point for any arbitrary oriented plane. So this is the discussion which we want to finish it. I hope you will be able to appreciate how we have derived it, and perhaps this should give you more confidence in the things to learn. Now in the next discussion, we'll be continuing forward with the ideas of transformations. I mean, the coordinate axis is say given in this form right now, but in we may require to orient it because of certain properties of the material or the application. Then what would happen to the stresses and strains under that transformation? So we'll be discussing that in the immediately after this. So let's come back for that. Thank you. So hello everyone. We'll now be discussing the concept of coordinate transformations because that will help us get to this idea of stress transformations and principal values of stress and so on. Okay, so let's see first of all the motivation behind doing this. Consider you have this piece of solid and it has some sort of fibers inside it, maybe by design or naturally. I mean, for example, a material like bone or wood has fibers like this along a particular direction, and then you will have obviously one so-called coordinate system, but it may be more convenient to work in a coordinate system which is perhaps inclined like this. Okay. Just because of the way the solid is, it may be more convenient to say define the value of stress and strain in terms of the x dash y dash coordinate system as compared to the xy coordinate system. So in this case, what do we do? So for example, if we have the values of stresses or strains, okay, say Exx, Exy, Exz, and Eyx, Eyy, Eyz, and Ezx, Ezy, Ezz, we want this to transform into the new coordinate system, strains or stresses, and this would then be Exx dash in the new coordinate system, Ex dash y dash, Ex dash z dash, Ey dash x dash, E y dash y dash, E y dash z dash, E z dash x dash, E z y dash dash, E z dash z dash. So in this figure which I have drawn, the z and z dash are the same. Okay, but in case they were different, what would that new stress and strain look like? And that's what the motivation about this transformation is. Now what we'll do is we'll try to first transform a vector, and then we'll try to just extend it to the case where the transformation of stresses or strains, in short a tensor, can be done. So let's see how we can proceed for this. Okay, let's start with the coordinate system, which is our own sort of, let's call it, let's call the purple one. Okay, so E2 hat is the unit vector in the x2 direction, E1 hat is the unit vector in the x1 direction, and E3 hat is the unit vector in the x3 direction. Now this is one coordinate system, and this is quite understandable to us. Now let's consider a new coordinate system. Okay, So this new coordinate system I'm drawing by a different color, x2 dash, x3 dash, x1 dash. So x1 dash, x2 dash and x3 dash is the transformed coordinate system or a separate coordinate system. The origin is definitely the same, but the axes, as you see, are very different from each other. And the unit vectors this time are e3 dash, e2 dash and e1 dash. Okay, so these are the two coordinate systems, and the basis vectors, as you have seen, is e1, e2 and e3, or in short ei and ei dash. Okay, so these are the basis vectors of these two separate coordinate systems, and let's see how we proceed in trying to understand this concept. First thing, we want to define what the cosine of the angles are. So we want to define that qij is equal to, so this is defined as cos of the angle between xi dash comma xj. Okay, for example, if you want to write what q12 would be, it would be the cosine of the angle between x1 dash comma x2, meaning it would be the angle between x1 dash and x2, which is this particular angle. Okay, so the cosine of this angle will be q12. Similarly, if we have q32, this would be cosine of x3 dash comma x2. This time the angle would be between x3 dash is this one and x2. So this is the angle we are talking about. Okay, so this is how you can find all the combinations, and clearly there will be 9 combinations of it. Okay, so qij can take up 9 values, ijk again go from 1 to 3. Okay, so let me just rub out some parts. Now what you have to do is look at, I will write out in words, look at e1 dash in the ei frame. What it means is this: look at the x1, x2, x3, the purple coordinate system. This is the coordinate system, and just look at one vector which is e1 dash, this one. Okay, in this coordinate system, and forget about the other x2 dash, x3 dash, or e2 dash or e3 dash. Now this vector e1 dash, since it is lying in the purple coordinate system, it can be written as e1 dash is equal to, remember we were writing it as e1 plus e2 plus e3. Okay, we can write it as a combination of linear combination of e1, e2 and e3. This was the whole concept of basis vectors which we had learned earlier as well. Similarly, the vector e2 dash can be independently written, okay, in terms of the same e1 hat, e2 hat plus e3 hat, and e3 dash is equal to e1 hat plus e2 hat plus e3 hat. Okay, so this is how the three vectors are. Now if you want to fill in what should be, what should be the scalar values of these, so let's start with an easier case. Okay, if you have to write e2 dash, okay, and in terms of e1, e2 and e3, you would write it as q21, q22, q23. Similarly, this would be q11, q12, q13, q31, q32, q33. First of all, can you think of a reason why this should be true? Okay, I mean, I can give you a straightaway answer that if you dot e1 hat dash with e1, okay, you should get the angle between e1 dash and e1, right? So you should essentially get this particular angle, and this particular angle is q11. Okay, so this is how we are able to write all the values which you see over here. So you can do this math for any of the 9 combinations and you will see that this holds true. Okay, let me just now remove this. We have used this definition of qij, cosine of the angle between xi dash, and this is not new. I mean, I think in the previous discussion you have learned about the n vector and how it was used in defining the traction vector for an oblique plane. So this concept has come up over there. Okay, now this is just like writing the green vectors. These are green ones, the dash ones, using the purple ones. But you can do the reverse as well, meaning look at E1 in the E1 dash frame, or look at E1 in the green frame. So if you do that, you will get an opposite transformation. This, by the way, can be written as E1 EI dash is equal to QIJ EJ. Okay. Similarly, if you want to write EI, that would be QJI EJ dash. Okay. So this is something you have to do. Use the same reasoning which I have done above and try to come up with this. If you come up with this, it is a proof that you have understood it. If you are not able to come up with this, means that you have not understood what is taught just above it. A knowledge which cannot be used is not very useful. Practically, it's useless. So let's try to ensure that whatever we are learning is actually useful and you can actually apply what you learn somewhere. Okay. Now the opposite transformation can be written in this particular form. Now let's come back to this figure and draw an arbitrary vector. Let's call this vector as, sorry, too thick. The red one is better. Okay. It's called a vector V. Okay, a vector, as we have shown. Vector, again, a quantity which has magnitude, direction, and it obeys certain laws of vector transformation. Now this vector V has two frames in which it can be seen. It can be seen in the purple frame and it can be seen in the green frame. Okay, so let's start with the purple frame. I want to write the vector V using the purple frame. That would be V1 E1 hat, V2 E2 hat plus V3 E3 hat. this is vi ei hat. Similarly, the same vector v, the red colored vector v, okay, can now be written in terms of the green coordinate axis, in terms of e1 dash, e2 dash, and e3 dash. So let me now write v1 dash e1 dash plus v2 dash e2 dash plus v3 dash e3 dash. This is vi dash ei dash. Okay. So one of the things which you should note is obviously v1 and v1 dash and v2 and v2 dash are generally not the same. The reason is we don't know. I mean, these are two independent ways to write it. Okay, this and this are two independent coordinate systems. So there is no reason v1 and v1 dash would be related, at least until now. Okay, so these are the two things. The same vector is written in terms of two separate set of basis vectors, two separate coordinate systems. Now what we want to do is we want to substitute this this one, we want to substitute this into this. Okay, let's see what that gives us. This will give a v which is vi, and then ei is qji ej dash. Okay, so this is what we have right now. But now you look at this one and this one. This too should give you, okay, I'll just write it as vj dash ej dash. Okay, I am writing this because I can write it, since I will go from 1 to 3 and j will also go from 1 to 3. I can do that. Now you see that v is equal to vj dash ej dash, and v is also equal to vi qji ej dash. These two things, these green two things, they combine and imply that vi, sorry, yes, vi dash is equal to qji vj. Let's see whether this can actually be written. I see, yes. So with these green things, you can say that since both of them are v is equal to this and v is also equal to this would imply that vi is equal to, vi qji is equal to vj dash. Okay. Now you can interchange I and j in these two. Okay, interchange I and j in these two to write this as vi dash is equal to qij vj. You can do this interchange because both of them go from 1 to 3. Okay, so once you proceed with this particular knowledge, you will have to go with the vi dash is equal to qij vj, and once you now repeat the same exercise, this time what do you want to do? Let me show in red. This time you want to substitute this into this, okay, and proceed in a similar manner to get vi is equal to Qji Vj dash. Okay. So these are the two relations which you have got. This is something which you should do. If you are not able to derive this using the method which I have shown in red, that means you have not understood what we have done until now. Okay, so please derive this and only then you should move ahead. Okay, so now let's sort of move ahead and use what we have just done until now. Okay. Okay, so there's two relations which we have just derived. Vi dash Vi is equal to Qji Vj dash and Vi dash is equal to Qij Vj are the so-called transformation laws for the Cartesian components of a vector. Meaning, if you have a vector defined in the dash system, okay, you can convert it to the undashed system. And similarly, if you have a vector defined in the undashed system, you can convert it to the dashed system. So these are the two transformation laws that will actually help you convert a given vector in the purple system to the green coordinate system, or a vector which is defined in the green coordinate system to the purple coordinate system. And so that is the say relationship between v1 and v1 dash and so on. Okay, and similarly v2 and v2 dash and v1 dash. So all these will come into play over there. So this is the transformation law which you have just derived for a vector. One of the things which you should definitely know, that no matter in which frame of coordinate system you define your vector, the red vector, its magnitude and direction will remain the same. I mean, if the vector, this vector is of size this, it will continue to remain of this size. If the vector is oriented exactly in this direction, it will continue to be oriented in this direction. The vector itself does not change. The representation in terms of these scalar quantities will change, and that will take care of it. For example, the magnitude should be v1 square plus v2 square plus v3 square whole square, or v1 dash square plus v2 dash square plus v3 dash square under root. So both of them should be the same magnitude, and they will be, because the vector itself is not changing, only its representation in different coordinate systems is changing. Okay, now one of the good things about our course or our discussions is that our coordinate systems are orthogonal. Okay, so this, what we have shown, the coordinate systems may not be orthogonal, meaning the angle between x1 and x2 and x1 and x3 may not be 90 degrees. Okay, similarly the angle between x1 dash and x2 dash and x2 dash and x3 dash will not be 90 degrees, may not be 90 degrees. This is the most general case which we have learned until now. But since we know that most of our coordinate systems will actually be orthogonal, in the sense x1 x2 will be 90 degree, the angle between x1 dash and x2 dash will be again 90 degree, so that makes life slightly easy for us, and it will have certain properties for this Qij, that cosine matrix which we have learned. So let's see how that works. I'll try to give a sketch about it. So let's first use this red transformation which we have. So let's call it Vi is equal to Qji Vj dash. Now I want to put this Vj dash over here. So Qji will be write it as Vj dash is equal to Qjk Vk. The reason we are doing is because we do not want to get confused between the I of this and the I which is already existing over here. So we are using k as this dummy index which does exactly the same thing which I was doing. So here Vj dash can be replaced and this will now become Qjk Vk. Okay. Again, I, j, k all go from 1 to 3. Okay. Now there is another sort of function which is required at this stage, and that's called the chronicle delta function. So let's slightly learn about it. We have, I think, mentioned about it once before, but this is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. Okay, so this is essentially a 1 0 0 0 1 0 0 0 1. This has certain properties. For example, delta ij is equal to delta ji. Okay, meaning delta 1 2 will be the same as delta 2 1, which is 0. Delta 3 2 will be the same as delta 2 3, which is equal to 0. And delta 1 1 will be equal to delta 1 1 will be equal to 1. So this property holds. Now look at the other property, that's delta II is equal to 3. Let's see how this can be done. So delta II has I repeated. So delta 1 1 plus delta 2 2 plus delta 3 3 is equal to 1 plus 1 plus 1 equal to 3. Okay, so that shows this property. If this was actually delta II dash, this under root which you see, under a bar which you see, this tells you that there is no summation over the repeated index. And if there is no summation, it can only mean that it is either equal to delta 1 1 or delta 2 2 or delta 3 3. In all the three cases, the answer of this should be equal to 1. So delta I bar is equal to 1. Now look at the other property. Just remove this over there. The other property which you have is delta ij is equal to ai. So let's look at delta aj. What is the repetition over j? So delta I1 plus delta I2 plus delta I3 Okay. Now for I equal to 1, delta 11 plus delta 12 plus delta 13 this is equal to a1 because this and this is 0, this is equal to 1, and this will be equal to a1. So for I is equal to 2, delta 21 a1 plus delta 22 a2 plus delta 23 a3. This is 0, this is 0, this is 1, and this is equal to a2. Similarly, for I equal to 3, you will get delta 31 a1 plus delta 32 a2 plus delta 33 a3. 0 0 1 a3. So this what you have is actually equal to a1 a2 or a3 depending on what ai is. Hence you can write that delta ij aj is equal to ai, and that is the property which you have over here. Okay, exactly in the same way you can use delta ij ai is equal to aj. Please do and prove this one. Okay, this will show that you have understood the previous case. Okay, now let's move to the next property about this chronicle delta. Okay, the next property is delta ij delta ajk is equal to aik. Let's see, the repetition is over j, so this would be delta I1 A1k plus delta I2 A2k plus delta I3 A3k. Okay, now for I equal to 1, k equal to 1, this would be delta 11 A11 plus delta 12 A21 plus delta 13 A31 0 0 1, so this will be equal to A11. For I equal to 1, k is equal to 2, this would be delta 11 A12 plus delta 12 A22 plus delta 13 A32. This is 1, this is 0, this is 0, this is A12. Okay, and so on. So what you will see is that this will always come out to be equal to A11, mean depending on what I and k are. So if I is 1, k is 2, you will get a A12. Okay, so that is how this property is derived. So delta ij ajk is equal to aik, and similarly you will have, you should actually go with all the 9 terms and verify this, but I think you can see what I'm trying to do and how I am arriving at these properties. Similarly, you will have another property which is delta jk aik, and that is equal to aij. Okay, so this particular property you can derive in the exact same way which we have discussed. And lastly, you would have delta ij aij, that would be equal to aii. So let's see how this happens. Repetition is over, sorry, ij. Repetition is both over I and j. In this case, first repeat over I and then repeat over j, or you first repeat over j and then repeat over I, whatever works. So let me first start with j. Delta I1 ai1 plus delta I2 ai2 plus delta I3 ai3. Now in each of these 3 terms you will see there is I which is repeating. So just focus on this term for now. Delta 11 a11 plus delta 21 a21 plus delta 31 a31. Now look at the second term, delta 12 a12 plus delta 22 a22 plus delta 32 a32. Now look at this last term, delta 13 a13 plus delta 23 a23 plus delta 33 a33. Okay, now many of these terms become 0, this one, this one, this one, this one, this one, and this one, and delta 11, delta 22, and delta 33 is equal to 1 each. This would make it a11 plus a22 plus a33, and this is what aii is. So that proves this particular property. Okay, and the last property is delta ij is equal to 3. So this property can be proven just by saying that, well, we already know this property, so in this one let's just put aij as delta ij, so that would make it as a delta ii, and it would be equal to 3, which you have just shown over here. Okay, So this is how these properties of the canonical delta function be proven. Now why we are discussing all this? Because we have to use this now. So let's see whether we are able to use it. Okay. I'm saying that using the properties of the canonical delta, this expression, the expression which is this one, can be written like this. Let's see if we can agree to this. Delta ik Vk is equal to Qji Qjk Vk. Okay. Now how is this true? It is true because this particular term can be written as Vi. Okay, and it is because of this property. Obviously J and K can be interchangeably used, so this is the reason why this is true. Okay, now let me just remove this. This implies that I can write Qji Qjk minus delta Ik is Vk. You see why we are doing is because we wanted all these forms. Okay, so it's not by coincidence that we are invoking certain properties and interchanging the variables where we can. Okay. Okay, now if since this is true for all Vk, okay, so this is the thing. I mean, if a b is equal to 0 and this has to hold for all b, this implies that a is equal to 0, and hence I say that qji qjk is equal to delta ik. Okay, so this is what we have got until now, and this is a property of the cosine, so the so-called the transformation matrix. Okay, I hope you could have seen that over here. The transformation e1 dash e2 dash e3 dash could be written as qij e1 e2 e3. Okay, so this can be converted to this using by multiplying with this transformation matrix. Okay, so this transformation matrix has this particular property which we have just derived over here. Okay, if you follow a similar procedure as this, okay, now instead of using this in this, try to do the reverse. Okay, meaning try to use this over here. In that case, you will arrive at qij qkj is equal to delta ik. Okay, don't eliminate vi dash, eliminate vi, the unprimed one, and this is something which you should do. Why? Again, for the same reason, that if you are able to do this, it means you have understood how this is done. If you are not able to do, meaning you have not actually understood what has been taught to you. So please do this, and if there's any doubt, feel free to ask me. Show me that this is what I have done and I could not proceed further. Okay, so these two relations which you see, which are sort of square bracketed, are called the orthogonality conditions. conditions which Qij must satisfy. And if you take the determinant of either of them, you will be able to get this. Okay. So this is something also you should verify. You should know what it means to take the determinant of the either of these two relations. You should be able to get this value. Okay. So I hope this discussion on coordinate transformation was helpful, and using this will be defining what a tensor is now. So if you have a scalar quantity or the so-called zeroth order tensor, the transformation law would look like this. Meaning it would not change at all its value. Say temperature, okay, the temperature in the purple coordinate system and temperature in the green coordinate system will remain exactly the same. Okay, and that's true for any other scalar. So that's one good part about scalars. There is no change in the value at all of it. Okay, now come to the vector which you have just learned. AI dash is equal to QIP into AP. This is called a first order tensor or a vector. This relationship you have just defined over here. This one. Okay, so I've just replaced J with P, and that's it. So the ith component of the vector A can be written in terms of this one. By a similar method, we can keep on extending this definition. A tensor will be written as QIP, QJQ, APQ. This is a second order tensor, and it's, well, just a matrix for us. And similarly, there is a third and fourth order. So let me just write out what a fourth order tensor would look like. That would be QIP, QJQ, QKR, QLS, APQ, RS. This is a fourth order. Okay. So a tensor is a matrix, in our case a 3 by 3 matrix, because it follows this transformation law. Okay, and that's the definition of a tensor. In fact, a vector is also a tensor. A vector is a tensor because it follows this particular transformation law. So in your textbook you have an example between which shows how transformation matrices are multiplied. So if you have a doubt, please refer to the example of transformation examples in your textbook in chapter 1. There you can see how numerical values are put and how actually you can perform these operations which you see over here. Okay, so please see this if you have a doubt. And there are definitions of tensors. For example, if under specific transformations, If the values do not change, it's called, or the components remain the same, then it's called an isotropic tensor. So we'll see that when we refer to the elasticity tensor, which is a fourth order tensor, the connection between stress and strain, that we'll consider isotropy then, and we'll see that we'll utilize this transformation law then and show that the form does not change and the values will remain the same under any transformation. So we'll see that when that happens. Okay, so let's now that completes our discussion on transformation and a definition of Cartesian tensors. So in the discussion which follows this, we'll be learning about the principal values and the directions of symmetric second order tensors. So we'll do that as we proceed in this discussion. Thank you. Okay, hello everyone. In this class, we'll be discussing about the principal values for symmetric second order tensors. We have already seen that strain is a symmetric second order tensor because it follows the properties which we have just discussed, and symmetric because of the arguments which we made during the geometric construction. I am also stating, just for record now, that stress is also a symmetric second order tensor. It's a tensor because it follows the same properties which we have just discussed, and it's also symmetric. We have not actually shown that stress is symmetric for now, but we will very soon. So for now you can just keep on record that stress is a symmetric second order tensor. Now let's try to motivate what principal values are, why do we even need it, and so on. Okay, now think of a vector. It can be anything, 3i cap plus 4j cap units, okay, depending on whatever that vector is. So you clearly know the magnitude of this vector is 3 on the x-axis and it's 4 on the y-axis. Okay, and as you see, the magnitude is somewhat dispersed or distributed between the x and the y directions. Now if we ask ourselves what is the magnitude of this vector, the answer would be, it will be 3 square plus 4 square and the whole square root. That would be a value of 5. That's true. Now in what direction this 5 magnitude occurs? It clearly does not occur in the x direction because it's only 3 units in the x direction. It clearly does not occur in the y direction. Okay, so because it's only 4 units in the y direction. So this maximum magnitude of 5 units, in what direction does that occur? Well, the answer is that it occurs in this direction, the green direction. Okay, and you can call this as x dash and this is y dash. So now if you look at this vector, it is entirely lying on the x dash direction, and hence the entire magnitude of 5 units will be lying on the x dash direction, and clearly in the y dash direction it will be 0. Okay, now look at another possibility. You could have y double dash and x double dash in this form. In this purple axis, the entire magnitude of 5 units is lying along the y double dash axis and 0 along the x double dash axis. Okay, so this is the so-called principal value and the direction in this system. Now think of it in terms of the coordinate transformation. You had the black coordinate system in which you had a red vector which was of magnitude 5 units, and there were components of this magnitude along both the x and the y axis. You now rotated this to the x dash y dash system and you found you could come up with a coordinate system in which the entire magnitude of this vector is concentrated along one direction, one principal direction only, which is the x dash direction. There is another principal direction as well, which is y dash, but there is no component of the magnitude along that. Similarly, you could have also done a coordinate transformation from the black to the purple, in which the entire magnitude of this vector would have lied along the y double dash principal direction. Okay, so this is important, okay, to find the maximum magnitude and in what direction that is there. This was a vector, and hence this visualization was easier. Think of now a three-dimensional solid body. You have a point of interest, and that has a stress sigma ij. You know what this is? It's a 3 by 3 system, which would be sigma xx, sigma xy, sigma xz, and so on. Okay, you will have these 9 values at this point of interest, and if someone asks you what's the maximum value of stress at this point, you would not have a straightaway answer, because obviously the stress at this point is distributed among these 9 values. Well, some of them may be 0, some of them may not be 0, but it's distributed among 9, just like in a vector it was distributed along these two directions. So you have to now come up with one single value, what was 5 units in this case, for this question, that what's the maximum value of stress at this particular point and in what direction that occurs. Like in this one, the 5 units occurs in this red direction, green direction, or the purple y double dash direction. So that is what we are trying to understand. Why is it important? It's important because mostly the failure theories use principal maximum values. Okay, recall any failure theory like the principal stress or the Tresca criteria. You will have those sigma 1, sigma 2, sigma 3 sort of terms. So these are the maximum values which stress at a point can take, and these failure theories will only be able to predict the failure at this point or not. They will only be able to tell you whether failure has happened at this particular point or not for the whole body in general. Okay, so that's the motivation of why we have to learn about principal values and coordinate transformations in this system. Okay, and that's what we should do. For example, if you have a piece of paper, okay, and then you fold it into half, okay, fold it into half, and then you press again on this particular line, you will get half of this paper like this. Now if you want to tear it, okay, it will be very easy for you to get a tear like this, straight line. If you don't press, if you don't fold over and don't press, you will not get a straight line when you are trying to tear a piece of paper. That happens because this becomes a plane of weakness, okay, and hence the strength of this piece of paper in tearing becomes very weak in this direction, and hence you may require certain transformations depending on how you are trying to tear a piece of paper. For example, if you want to have a cut like this, you will have to fold like this. Your coordinate system will be like this, but then you will have to transform it into a new system in this form and then find the principal values and rotation concepts over there. So let's see how that works in theory, and we'll obviously be very soon coming up in the application in what we are trying to learn. Okay, so let's go with the theory, which you should have seen by now, perhaps in your course in linear algebra in your undergraduate or some sort of other mathematical concept. Okay, the direction determined by the unit vector n is said to be a principal direction or eigenvector. Principal value is also called the eigenvalue of the symmetric second order tensor Aij if there exists a parameter lambda such that Aij is equal to lambda ni. So you may have learnt about this, and lambda is then called the principal value or eigenvalue. So Aij can be any symmetric second order tensor. Okay, stress or strain are the two tensors which you are aware of, though we are still to prove the symmetry of the stress tensor, but for now you can just take it as a theory. Now this equation which you have just, so this is how it is defined. Okay, this thing is how it's defined. Now you can write this term as Aij nj minus lambda ni equal to 0. This can also be written as Aij minus lambda delta ij nj is equal to 0. This can be written because delta ij nj is equal to ni. This is something which we have proven before, and that has been employed over here. Okay, so if you look at this equation which you have just derived, it's a homogeneous system of linear equations. Okay, the unknowns are n1, n2 and n3. Clearly at a point at which all this is being done, the stress and the strain tensors are definitely known. Okay, now this system, let me call it this system of linear algebraic equations will have a non-trivial solution if and only if the determinant of its coefficient matrix vanishes. This would imply that the determinant of Aij minus lambda delta ij is equal to 0. Now let's see this statement once more. A system of linear algebraic equations will have a non-trivial solution if and only if the determinant of its coefficient matrix vanishes. So let's take two examples and see whether this is true. Of course, it's a theory from an earlier subject, but you should still be able to write it. So let's put this equation as what? Y is equal to 2x. Okay, y equal to 2x, and then let's put another equation over here as y equal to 3x, And in this case, let's put another equation as 2y equal to 4x. Okay, let's see these two cases. So you would have y minus 2x is equal to 0, y minus 3x is equal to 0, and you should have 1 minus 2 and 1 minus 3, yx equal to 0, 0. So this is the system of linear equations in the first case. Okay, and let's see what is the other case. The other case is y minus 2x is equal to 0, 2y minus 4x is equal to 0, and if you write it, you will get 1 minus 2 and 2 minus 4 y of x equal to 0. Now if we calculate the determinant of the coefficient matrix, in this case it should be what? Minus 3 minus minus 2. So this should be minus 1. In this case, the determinant of coefficient matrix should be 1 minus 2, 2 minus 4. This should be minus 4 minus minus 2, which is equal to 0. Okay, so this is the situation which you have in front of you. The system of linear algebraic equations will have a non-trivial solution if and only if the determinant of its coefficient matrix vanishes. So if the determinant of the coefficient matrix did not vanish, then it meant it had a trivial solution. Okay, and what is that trivial solution? That trivial solution is 0, right? 0 comma 0 is the trivial solution. Over here you have definitely one solution which is there, 0 comma 0, but then you have infinite number of other solutions. Okay, like every point over here is an infinite, and hence it is said to have a non-trivial solution. So it's not necessary that it will only have infinite number of solutions, but the idea is it should have some non-trivial solutions if you have the determinant as 0. So this is one example which you can see. Okay, so which validates this theory. Of course, you can take a larger system, you can take more number of equations. I've only taken 2. You can take 3 and just play with it and see and convince yourself that for non-trivial solutions the determinant must be of the coefficient matrix must be equal to 0. Okay, now let's see what this means over here. I just want to write it like this: determinant of A11 A11, A12, A13, A21, A22, A23, A31, A32, A33 minus lambda of delta ij. Delta ij, if you remember, is lambda 0, 0, 0, lambda 0, 0, 0, lambda. So delta ij is the identity matrix, and this must be equal to 0. This implies that the determinant of a11 minus lambda, a12, a13, then a21, a22 minus lambda, a23, a31, a32, a33 minus lambda is equal to 0. Okay, and now you want to find the determinant of this equation. So that would be a11 minus lambda, a22 minus lambda, a33 minus lambda, minus a23, a32. Okay, do remember, because it's a symmetric tensor, so some of these values should be, and that's what will help you in certain simplifications. So we are not calling those simplifications now, but the red ones are same, the green ones are same, and the purple ones are also same. Okay, so that's the first term. Now you want to write it as minus
A12, A21, A33 minus lambda minus A31, A23, and then you will have a plus A13, A21, A32 minus A31, A22 minus lambda is equal to 0. Okay, now if you look at this equation, you will clearly see that it will be a cubic in lambda. It's a cubic equation in lambda. Okay, so if you expand and solve it, you should do that now. Please expand this equation and try to write it as a cubic equation. You will be able to get minus lambda cube plus I1 lambda square minus 2a lambda plus 3a equal to 0, where IA is equal to AII equal to A11 plus A22 plus A33, A is equal to AII AJJ minus AIJ, and 3i is determinant of Aij. Okay, so please verify this and proceed ahead only once you are able to write this, all these three things and the cubic equation in this particular form. Okay, I have done the very easy part for you. For example, if you look at this minus lambda minus lambda minus lambda, their products will give you a minus lambda cube. Okay, so my easy job is done. But if you want to write the square ones, you will have to club the certain terms together and see how that goes. Okay, let's see. Okay, so once this is done, you can write this in terms of a cubic equation in lambda. Remember what lambda was? Lambda was the eigenvalue or the principal value or the so-called maximum value of stress at that given point where that stress is given, or the maximum value of strain at that given point where the strain tensor is specified. Now, because it's a cubic equation, you clearly know that it won't be one value like 5 in this case. Okay, it will be 3 values because it's a cubic equation. So at one point you should have at maximum of 3 principal values for stress or strain. Okay, now there are some interesting parts about this. One is that this 1a, 2a and 3a are called the fundamental invariants. Of the tensor Aij. Okay, so that means that this equation, these values will not change under any transformation. I will show that to you with an example in a minute. Okay, and the roots of this equation will give you lambda, and each of these lambda we must back substitute into this equation, put that one particular lambda and find what should be the value of n, meaning that maximum value which you have achieved is in what direction, because n is the direction. Okay, just one more word, this is called the characteristic equation. Okay, so if I ever ask you put it in the characteristic equation and find, you should know what to do. Okay,
So there are certain combinations, like if what if lambda 1, lambda 2 and lambda 3, which are the three roots of this equation, are all distinct, sometimes two of them may be common and so on. So we'll see all that when certain examples prop in. But the idea of invariance and principal direction should be clear. So what I'll do now is I will take an example from the your textbook and show it to you whatever we have learned. Okay. So let's first of all take a symmetric second order tensor that is given as this is example from your textbook. So that is given as 2 0 0 0 3 4 0 4 minus 3. Okay, clearly it's symmetric and it's second order, just like stress and strain. So it could have been stress and strain, but I'm just not referring to it right now. Okay, so if you had to now find the principal values, you would have to basically solve this equation, this characteristic equation which you have. Okay, and for solving that you will need the value of I this sorry 1a 2a and 3a. Okay, so let's do that first. So 1a would be a11 plus a22 plus a33, basically the diagonal term. So this is equal to 2. Okay, so 2a is equal to half of aii ajj minus aij aij. So this also, if you expand, okay, I will show you how that can be done. That would be a11 plus a22 plus a33. Okay, again it will be a11 plus a22 plus a33 minus this would be now 2 times. Okay, so aij aij. So you first expand it in ai1 ai1 in j. Okay, then ai2 plus ai2 sorry ai2 ai2 plus ai3 ai3. Okay, then each of these three terms will give you three more terms, that they will be a11 a11 plus a21 a21 plus a31 a31. Similarly, this would be a12 a12 plus a22 a22 plus a32 plus sorry a32 and so on. So this value should come out to be minus 25 for you. Okay, do this. Okay, don't just believe me because the author in the textbook says and I says. You should do it and see that you get this value. And similarly, the 3a should be very simple. It's just the determinant of this. So determinant of this is 2 into what, minus 9 minus 16, and the rest of it is 0. So this is minus 50. Okay, now once you put 1a 2a and 3a in the characteristic equation, you should get that equation as minus lambda cube plus 2 lambda square minus or say plus 25 lambda minus 50 equal to 0. Okay, now if you solve this equation, you can do some calculations with it. You will be able to, first of all, you should know how to solve this. Now is the time to pause the video and try to solve this. What should be the three roots of this equation? Okay, so those values will come out to be lambda 1 is equal to 5, lambda 2 is equal to 2, and lambda 3 is equal to minus 5. These are the three principal values of this aij. We do not know its direction now. Okay, just like for vector it was 5 units, so we exactly knew in what direction it was. But for this aij we don't know. Well, we know that the maximum value can be 5, 2 and minus 5, but we don't know in what direction this will happen. So the way to find the direction of it, you have to take it one by one and say in what direction it will happen. So let's now take, for example, lambda 1 equal to 5. Okay, first value. We want to find what is the direction for this. What is the direction where this principal value occurs? So for this, one has to substitute in this equation. Okay, you have to put lambda is equal to 5 over here. So let's see how we can do that. You write aij minus lambda delta ij nj is equal to 0. This would mean that aij is what? 2 0 0 0 3 4 0 4 minus 3 minus lambda 0 0 0 lambda 0 0 0 lambda, and nj would be n1 n2 and n3. Okay, so this is a system of 3 equations, and you can write it in this particular form. Now you want to say that 2 minus lambda into 0 0 0 and 3 minus lambda is 3 minus into 4, and then you can have 0 4 minus 0 is 4 minus 3 minus lambda. Okay, let me just check it once. Okay, just to be sure. So 2 minus lambda, 0 minus 0, 0 minus 0. Okay, 0 minus 0 is 0. 3 minus lambda is 3 minus lambda. 4 minus 0 is 0. 0 minus 0 is 0. 4 minus 0 is 4. Minus 3 minus lambda is minus 3 minus lambda. Okay, this is equal to 0. Now you want to write it as 2n1 minus lambda n1. Sorry. Yes. So it would be 0 0 0. Let's see how we write it. 2 minus lambda into n1. The other terms are 0, so this is equal to 0. Then you can have 0 into n1 into 3 minus lambda into n2 plus 4 n3 is equal to 0, and then 0 into n1, then 4 into n2 minus 3 plus lambda into n3 equal to 0. Okay, so let's see if we can actually solve this. But lambda was actually equal to 5, right? So we should have just written it as 5. Okay, anyways, never too late. So this is what, minus 3n1, and let me just show it by a superscript, because this lambda 1 is equal to 5. There are two more lambdas, 2 and minus 5. So this superscript will show that I am only referring to lambda 1. Okay, so minus 3n1 is equal to 0. The next equation should be minus 2n2 of 1 plus 4n3 of 1 is equal to 0. Eight n3 equal to 0. Okay, now if we want to solve this, so there are 3 unknowns and 3 linear equations. It should be very easy to solve this. That would give us the value of n1, n2 and n3, but remember this is the vector n1.
sorry, the direction of this is n1, and this would be n1 I cap plus n2 j cap plus n3 k cap. Obviously direction vectors are always normalized, so it will be n1 square plus n2 square plus n3 square. So this should come out to be plus minus 2 times e2 plus e3 by root 5. Okay, so this is the direction along which this symmetric second order tensor will take the maximum value of 5, or the principal value of 5. You have to now repeat, and definitely repeat, not skip, finding the direction for principal values of lambda 2 equal to 2 and lambda 3 equal to minus 5. Okay, so n2 for lambda 2 will come out to be plus minus e1 hat, and n3 will come out to be plus minus e2 hat minus 2 e3 hat by root 5. So one of the things which you can verify, you should verify, is that these directions, 3 directions, are mutually orthogonal. How would you verify? Just take a dot product between any 2 combinations. How many combinations which you will have? Okay, so you will have n1 with n2, n1 with n3, and n2 with n3. Okay, all these combinations take a dot product, and you will find that the products actually come out to be 0. That will ensure that it's mutually orthogonal. And this also tells us this idea that the principal directions are always mutually orthogonal. Okay, so whatever be the principal direction, for example, in this case, let's see the vector, because vector is easy to visualize, that's why I bring you back. So if the original axis was x and y, the new transformed axis x dash and y dash will be orthogonal mutually. And similarly, the other combination x double dash and y double dash will also be orthogonal. So the principal directions are always mutually orthogonal. Okay, and this is an example through which you have also showed this. Now, I also want to prove to you that these invariants, which I had called 1a, 2a, and 3 over here, are actually invariants, in the sense they do not change their value under any transformation. Okay, so what will I do? I will take the same symmetric second order tensor, put it under a transformation, and then get a new matrix. Okay, new transformation, and new aij dash. So, and how will that happen? It will happen according to this law. Okay, this is, so I will put this a p q as my given matrix, and I will get this transformed tensor, and then I will show to you that those invariants don't actually change. So let's do that. So you had aij already. You want to now get you have a transformation matrix. So that transformation matrix, let's call it as 0 to root 5, 1 by root 5, 1 0 0 0 1 by root 5 minus 2 by root 5. Aij dash will be equal to 0 to root 5. This is a transformation which you should have done from the solved example of your textbook at the end of our previous discussion, or at least a similar transformation. How it's done is something which you should be knowing. So what is A? Ij is 2 0 0 0 3 4 0 4 minus 3, and then the transpose of this 0 2 by root 5 1 by root 5 1 0 0 and 0 1 by root 5 minus 2 by root 5. Okay, so once you do this, you should get Aij dash and verify this, that you should actually do this row by row multiplication and get this. Okay, don't leave it for the last moment. This should give you a 5 0 0 0 2 0 and 0 0 minus 5. And just to write it, what was the original untransformed matrix? That was tensor 2 0 0 0 3 4 and 0 4 minus 3. Now let's see, there are three invariants 1a, 2a and 3a, and I say that under any transformation these values will not change. So I will just take the easier one, which is 1a, to verify. So 1a, if you remember, is aii. Okay, that's a11 plus a12, sorry, a22 plus a33. What is 1a in this case? That is 5 plus 2 minus 5, that is equal to 2. What is 1a in this case? It is 2 plus 3 minus 3 equal to 2. Hence 1a did not change under transformation, and it's not that this transformation is somewhat special. It could have been any transformation and the sum of diagonal elements would have remained exactly the same. Okay, same you can do and verify for 2a and 3a as well. Under any transformation these values will not change, and hence they are called invariants. Okay, so this is the concept of principal values which you have just learned, and if you want to now sort of identify, let's put it this way, it is possible to identify a right-handed Cartesian coordinate system, because since this is the system we have been working with, and this is, as you know, was mutually perpendicular, such that each axis lies along the principal directions of any given symmetric second order tensor. So such axes are called principal axis. Okay, and the basis vectors are now n1. Remember what n1 was? It was the direction of the lambda 1 principal value. This has now become a basis vector. I'll show it with a diagram. So if you had this original coordinate system which was looking like this, say x2, sorry, x Now the new coordinate system, which is x2 dash or n2, this can be n1 or x1 dash, and say this direction can be x3 dash or n3. Okay, so this is the idea that if you had the black coordinate system x1, x2, x3, you can transform your coordinate system in such a way that you have all the values of this tensor transformed only along lambda 1, lambda 2 and lambda 3, meaning you could have aij as this, transform it, let me use the correct color, transform by a suitable transformation matrix, and then you will have only lambda 1 0 0 0 lambda 2 0 and 0 0 lambda 3. Okay, so this was your aij, this becomes your aij dash, and this is what is the so-called principal values lambda 1, lambda 2 and lambda 3, and clearly in the other directions, as you see, the values are all 0. And just like in the vector case you had seen, the maximum value was either along x dash and y dash had 0 component, or in the other case y double dash had all the magnitude and x double dash had 0. So only along the principal direction you will have the value. All the shear terms will become 0. Okay, so these are sort of extremal properties, and they will have their own directions, as we have seen in this example. For the sake of mathematical simplicity, we always put lambda 1 greater than lambda 2 greater than lambda 3, even if it is not the case, like over here. Let's look at what lambdas did we get. Yeah, we got lambda 1, lambda 2 and lambda 3 as 5, 2 and minus 5. Well, in this case it's already satisfying lambda 1 greater than lambda 2 greater than lambda 3, but in case it is not, just interchange them at the end, so that lambda 1 is the largest, lambda 2 is the smallest in between, and lambda 3 is the smallest, if you do get out lambda 1, lambda 2, lambda 3 in that form. So we always try to maintain it in this particular form, and the usefulness of this form you will see later on when we discuss the Morse circle. Okay, now this concept obviously you have now learned, and it seems it's easy. From here on, it's only a small step ahead of, we want to say, introduce the concept of principal strains, yeah, and transformation in the learning of strain. So what do you have to do? Let's go for strains. First is the transformation. How do you transform? At any given point, you have the strain tensor given, you can transform it according to this law, which you have just learned before. Okay, and qij we have already seen is cos of xi dash comma xj. Okay, so this is it. I mean, if there is, say, let me show it to you once, how this q can also be taken. So if you have this x-axis, you have the y-axis, okay, and you have this new system as x dash and y dash. The angle is theta, over here, so it's a rotation by theta. Clearly the axes are mutually perpendicular. Now if you want to find the transformation matrix for this, let's see, q ij will be equal to q11, q12, q13, Q21, Q22, Q23, Q31, Q32, Q33. What is this? Look at this. It is cos of x1 dash and x1. Let me just write it separately. Q11 is cos of x1 dash x1. Q12 is cos of x1 dash x2. Q13 is equal to cos of x1 dash x3. Q21 is equal to cos of x2 dash comma x1. Q22 is equal to cos of x2 dash comma x2. Q31 is equal to cos of x3 dash 1, sorry, x1. Q32 is equal to cos of x3 dash x2, and Q33 is equal to cos of x3 dash x3. Let's see what these values should be. What is the angle between x1 dash and x1? So this is clearly x1, this is x1 dash. Okay, and so let me just use the y and z only. So this is x2 and this becomes x2 dash. Okay, x3 and x3 dash are the z axis, so they are unchanged. They remain the same in both the systems. So what's the angle between x1 dash and x1? That's cos theta. What's the angle between x1 dash and x2? Okay, that's 90 degree. Okay, x1 dash and x2. So this should be called x1 dash. Okay, x1 dash and x2 is this particular angle, and that's cos of 90 minus theta. What's the angle between x3 dash and x3? That's 0. What's the angle between x1 dash and x3? x1 dash and x3 will be cos of 90. Okay, and what's the angle between x2 dash and x1? That is cos of pi by 2 plus theta. What's the angle between cos of x2 dash comma x and x2? Cos of theta. What's the angle between x3 dash and x1? 90. x3 dash and x2 is again 90. Let's see. This should be equal to cos theta then. Q12 should be equal to sin theta. Q13 is equal to cos 90, which is 0. Q21 is equal to cos of 90 plus theta. Cos of 90 plus theta can also be written as sin theta minus sin theta. Again, Q22 is cos theta, and Q23 is where did it go? Oh, did we not write Q23? So okay, Q23 is the angle between x2 dash and x3. That would be cos of 90, which is 0. And then Q31 is cos 90, which is 0. Q32 is cos 90, which is 0. Q33 is also, sorry, Q33 is not 0 because the angle between x3 dash and x3 is 0, and hence this should be equal to 1. Okay, so this is your transformation matrix for this particular transformation, and all you have to do is just put it in this law, and we have already done a matrix operation before. It should give you the new strain component, so you don't have to ever remember a formula now. Now when you want to now discuss the principal strains, for example, okay, in this case you have to just proceed in the exact same way as before. You have to go to the characteristic equation, determinant of Eij minus E delta Ij. What is E? It's the principal strain, sorry. Okay, this is equal to 0. And now you will have the three invariants, as you would be aware, in the 1 2 3 system. So 1 2 3 system you can just call as the principal system. For example, E1, E2 and E3 are the principal values. They will have their own directions. Okay, so this is how you will be able to solve this. And in the transformed system, this will look like E1 0 0 0, E2 0 0 0, E3. This is the transformed. Okay, it's in the principal coordinate system. There will always be zero shear components. Okay, just because we have transformed it in such a way that all the magnitude of that tensor at that point only exists along three mutually orthogonal directions, which are the principal directions. Okay, now other than this, there is also this spherical and deviatoric strains. I'll tell you the physical importance of both of them. If you have a strain tensor, at any point, everything is at a specific point in the solid. You can decompose into volumetric or the spherical part plus a deviatoric. Okay, so the deviatoric strain component of the strain tensor is defined as 1 by 3 EKK delta IJ, and if you already know that this is this nu, okay, remember the first invariant delta IJ. And sorry, this was the spherical. I'm sorry, I should have written it. So this is the spherical, and obviously the deviatoric part would be the difference between the strain and the spherical. So strain obviously will be equal to the spherical part and the deviatoric part. So we will see this is the one which contributes to the volumetric change or volumetric deformation. It is an isotropic tensor. We will see how this is isotropic in a few minutes. It's isotropic because it will retain the same form under any transformation. Okay. So do remember when we actually discuss this. And then the deviatoric stress, this deviatoric strain, it is responsible for the shape change. It is responsible for volume change, and this is responsible for the shape change. Okay, so it's also mentioned that the principal directions of both the deviatoric strain is the same as that of the strain tensor. So you can perhaps try to prove this. If you have a doubt, please consult me. Show me what you have done. That the principal directions of the deviatoric strain are the same as those of the strain tensor. So show them that both of them will have the same principal values, principal directions. Okay, so please do this. If there is a doubt, you please show what you have done, and then I'll try to help you out.
Now you can, since you have learnt about principal strains, you can, sorry, transformation and principal values, the same can be applied for stresses. Nothing new. Okay. So that can be done by saying that sigma ij dash is equal to qip qjq sigma pq. Okay, and qij is the same. So this exact same thing can be done for transformation of stress. Okay, the stress at any given point is given to you. This is the one. And if you have a certain rotation transformation of the coordinate system, the new stress values will be same. Of course, it will have 1a, 2a, and 3a, which are the three invariants. And the principal values of this, you can say, will come out to be sigma 1, sigma 2, sigma 3. How do you get the principal values? Same as before. Put determinant of sigma ij minus sigma delta ij, where obviously sigma is the principal value. This should be equal to 0. Now this would mean that there is sigma cube minus 1a, first invariant, so sigma is the principal stresses, and the invariants are just like the previous or the general case which we had seen. The reason this is looking very simple because sigma 1, sigma 2 and sigma, remember, are in the principal coordinate system. So this I2 has become very short. Okay. And similarly I3 is equal to sigma 1, sigma 2, sigma 3. Okay. The shear terms are 0 in the principal system. So if you had like sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, sigma 3, 3, you have transformed into this system. Okay, transformed. And because this I1, I2 and I3 are invariants, so it's always easier to work in this system, right? Because it will have so many zeros in it. So that's why this I2 is looking very simple compared to what we had in the Aij case. Anyways, so this is how it would look like, and visually how this would work out. Well, you already know this is an X, there's a Y, there's a Z. Now you knew, or perhaps we're doing this already. So you had a sigma. So this was the undeformed sort of the given value. So this is the general coordinate system. You had a sigma x, you had a sigma y, you had a sigma z, you had tau xy, you had tau xz. Similarly, you had tau yx and you had tau yz. So I'm not showing the zx and zy, but that's the general coordinate system. How does it look in the principal coordinate system? Well, there is definitely no rotation. And C3 is one of the principal directions, 1 is the other principal direction, 2 is the other principal direction. So sigma 2, sigma 1 and sigma 3. This is the principal coordinate system. Okay, no shear terms appear in the principal coordinate system. So this is what it is. So this is the visualization part of it. This cube has now been transformed in a way such that only sigma 1, sigma 2 and sigma 3 are present. The other 6 components are definitely all 0.
Okay, now there is another issue which has to be dealt with right now, and that is about the stress and traction. We are coming back to what where we had left the discussion on strain. Okay, so let's look at the traction vector first. Let me draw a solid. We want to draw a sectioned solid. Okay, so this is a sort of sectioned solid. Sectioned in the sense we had virtually cut this into along a particular direction so that we could define all those internal forces and so on. So at this point you have, say, a given traction is Tn. Okay, area of this is delta A, this is the S surface. So this traction can be transformed along two directions. Sorry, this should be, the two directions can be a normal direction and then you can have a shear direction. Okay, so any vector can be transformed along the normal and the shear. There's nothing new about it. Okay, so let's do that. So the normal vector n, normal component, sorry, this n which you have in green over here can easily be found out, right? Because this n actually is also coinciding with the n direction, the outward normal to the small area. So if you take a Tn dot n, you should get this normal component, right? It's just cos theta term. And then the shear part of it will just be the, subtract the magnitudes. Okay. So because you knew that normal plus shear is equal to Tn whole square. Okay. Now let's write this normal component. Sorry, n is not a vector, n is a scalar. I keep on writing. This is Tn dot n, and this can be written as Ti of n n I. Let me show you why. You have a vector, say A is equal to AI I or A1 E1 hat plus A2 E2 hat plus A3 E3 hat. Similarly, you have a vector B which is BI EI dash, and this is equal to B1 E1 hat plus B2 E2 hat plus B3 E3 hat. Okay. Now A dot B will be equal to A1 B1 plus A2 B2 plus A3 B3. Okay, and hence this can be written as AI BI. So that's why the dot product can be written as TIN NI. Okay, because since Tn and n are both vectors. Now this TINI can be written as sigma JINJ into Ni, because we had derived for an arbitrary plane TIN is equal to sigma JINJ. Remember, we had done this derivation. So we have substituted TIN as sigma JINJ. Okay. Now if I want to write it in expanded form, first I will have to expand it for the j and then for I, or first for I and then for j, because both of them are repeating. Now here is a trick. I want to work in the principal coordinate system in which the shear terms will not be there, and hence I will only have sigma 1 1 sigma 2 2 sigma 3 3, which we call as sigma 1 sigma 2 and sigma 3. So we will then use it. Okay, we have done this choice of using a principal coordinate system after this just for the sake of simplicity. Otherwise, you know that it will have a lot more many terms. Okay, so for simplicity we are doing this over here. Now let's see what we do for Tn. Right, we want to find the shear. So n we have already found out, this is it, and the shear is, so let me just call it as principal coordinate system. That's n, that's n. Now we want to also find the shear component of the traction vector. Okay, so shear component can be found out, n has already been found out, all you require is this Tn. So let's put that Tn whole square is Tn dot Tn. That's true, right? If you have a vector A, you take a dot with itself, you will get a1 square plus a2 square plus a3 square. So that's what will happen. Okay, so let me just write that as sigma ji. We are using this now, sigma ji nj sigma k I n k. Reason for not using j again is that we don't want confusion in what the indices should be. Okay, so this has been written in this particular form. What you see that we have retained the I term because I has to be here. Let me just, should have been ti n ti n. Okay, dot product, and then this would be sigma ji nj, and the next one is sigma ki nk, sorry. Okay, so I am not like distorting what I should be, I'm only using j and k because both of them are dummy indices, so it should not actually matter. Otherwise it will be confusion between this and this, which is not intended. Okay, so once this is done, this can be again in the principal coordinate system. The shear terms will drop off, so there is no sigma 1 2 sigma 3 2 sigma 3 1 and so on. So this would be sigma 1 square n1 square plus sigma 2 square n2 square sigma plus sigma 3 square n3 square. Okay, now let me just sort of, and this was what s square plus n square is this. Okay, so s square plus n square can be written as this. So this implies that n, first I'm writing what we had found for the normal component. Then n square plus s square, this is n square plus s. Okay, according to this is equal to sigma 1 square n1 square plus sigma 2 square n2 square plus sigma 3 square n3 square. Now we want to write one more equation. The reason is because n is a unit vector. So since n is a unit vector, n bar square plus n2 square plus n3 square, which is the magnitude of this vector, must be equal to 1. So that's how the third equation has come in. Now you can see this as a system of linear equations. What are the unknowns? The unknowns are n1 square, n2 square and n3 square. Okay, so this is a system of linear equation, and you can solve it. There are few ways to solve a system of linear equation. You must be aware. One is called the Gauss elimination method, through which you convert a pivot
and then proceed accordingly. The diagonal has to be converted to 0. The other, for a smaller system like this, is Crandall's rule. Okay, so for a small system like this, you can go for either of them. So you have to do this. You have to solve the unknowns n1 square, n2 square, and n3 square and get this by any method you want, but you must be able to do this derivation yourself. So either by Crandall's rule or Gauss elimination method, whichever works for you. So s square, so n1 square will come out to be s square plus n minus sigma 2, n minus sigma 3, sigma 1 minus sigma 2. Let me let me write that over here. N1 square will be s square plus n minus sigma 2, n minus sigma 3, sigma 1 minus sigma 2, sigma 1 minus sigma 3, and 2 square is equal to s square plus n minus sigma 3, n minus sigma 1, sigma 2 minus sigma 3, and sigma 2 minus sigma 1, and n3 square will be equal to s square plus n minus sigma 1, n minus sigma 2, and sigma 3 minus sigma 1, sigma 3 minus sigma 2. Okay, so this is what you would get after you solve this system of linear equations. You have to do this. Don't proceed ahead without actually doing this. Okay, now you can rank your sigma 1, sigma 2, and sigma 3 like this. If they don't turn out in a problem like this, you can always interchange, so that whatever you call sigma 1 should be greater than sigma 2, should be greater than sigma 3. Now, one of the things which you should have notice is that n1 square, n2 square, and n3 square have to be all positive because it's square of a number. Okay, so it cannot be negative. So if you look at the denominator, this is positive. Sigma 1 minus sigma 3 will be positive. Sigma 2 minus sigma 3 will be positive. Sigma 2 minus sigma 1 will be negative. Sigma 3 minus sigma 1 will be negative. Sigma 3 minus sigma 2 will be negative. So this becomes a positive denominator. This becomes a negative denominator, and this becomes a positive denominator. Now, for n1 square to be positive, the numerator must be positive, which is s square plus n minus sigma 2, n minus sigma 3. This must be greater than equal to 0. For n2 square to be positive, the numerator must be negative because the denominator is already negative. So that would imply that s square plus n minus sigma 3, n minus sigma 1 is 0. Let me space becomes a concern, so let me just write down over here s square plus n minus sigma 3, n minus sigma 1 is smaller than equal to 0, and for n3 square to be positive, the numerator must be positive, which is s square plus n minus sigma 1, n minus sigma 2 is greater than equal to 0. Okay, so these are the three conditions which you have got. So what we want to do now is we want to make a plot that should be between n and s. Okay, so if you can see that all the three inequalities which are written over here are actually that of a circle.
Okay, so it's just like x square plus y square sort of a behavior, ax square plus by square, or whatever you want to call it. Okay, so it's the circle, and the center of the circle is something which we can easily see in this case. So let's draw the first circle and see how that goes. So n minus sigma 2, n minus sigma 3. Okay, so because sigma 1 is greater than sigma 2 is greater than sigma 3, so let's just call this as sigma 1, sigma 2, sigma 3. So this particular circle can be like this. The diameters of it are sigma 2 and sigma 3. Okay, the next one, which is sigma 1 and sigma 3. Okay, that's this particular one, the big one. Okay, this one, and the last one is sigma 1 and sigma 2, so it should be this particular one. Okay, didn't come out very well. Okay, so let's call this as circle 1, circle 2, and circle 3. So this is circle 2, this is circle 1, this is circle 3. Now they are not actually equalities. If you look at C1, it shows that S and N must lie outside or on this circle. Okay, it's greater than or equal to. So you will have basically everything outside this circle. Everything outside C1 circle. Okay, the whole space. Okay, now the second case, which it must also satisfy over and above the first condition, is that it should be within C2. Okay, S and N should be within C2. So C2 is the bigger circle, and it must also be outside C1 and within C2. So that would be, let me use this ink. Okay, so whatever it is in green is satisfying this and this. Whatever was in red was only satisfying the C1. Now you have a third condition, that S and N must be outside C3. Okay, so and be outside C1 and within C2. So that would be this part. So the purple part will satisfy all the three conditions. Okay. Okay. So this is what we have, the so-called Moore's circle, and it's a, what it gives you. It gives you the permissible value of n and s. So s and n must be in the purple zone, because that's the zone which satisfies all these three conditions which you have over here, 1, 2, and 3. So the purple one satisfies this, this, and this. Okay, so it gives you the admissible values of n and s, and they lie in this given purple zones. Now one of the things which you should also note, what is the maximum value of s, the shear component of the traction vector. Okay, that's half of this radius, so that can be half into sigma 1 minus sigma 3. Okay,
So this, as you have seen, is the discussion on principal stresses, and I hope this Morse circle and the derivation of it was very clear. It gives you this allowable values between n and s, and we can all will be using this very often. So just like the strains, we have the spherical and deviatoric part of stresses. So sigma ij is equal to 1 by 3 sigma kk delta ij. This is the volumetric part. The deviatoric part would be sigma ij minus 1 by 3 sigma kk delta ij. Okay, and the total stress, just like the previous case, would be sigma ij is equal to sigma ij hat. So the spherical stress is isotropic. We'll see what an isotropic tensor is very soon, and the idea is that it will remain the same in all coordinate transformations. We'll see that. Okay, and some of the other components, and just like the other ones, I mean, if you have a shape change, the deviatoric component would come into play. If you have a volume change, the volumetric or the spherical component of stress and strain comes into play. Now there are several other terms which are obviously important when you try to study the failure theories. So using these von Mises and other criteria, you can find out using the principal values what say von Mises stress is. Okay, so depending on whether there is a plasticity involved or whether it's a brittle material, you use different failure criteria. So I am not covering those things in this class, but you have a small section called spherical, deviatoric, octahedral and von Mises stresses in your textbook. You should do it. It's very much a part of the so-called syllabus, but I would not want to cover that over here. Okay, in the next discussion which we have, after which we will close the discussion on stresses, we will be discussing about equilibrium conditions. Okay, this is the part where we try to prove, we actually prove that the stresses are actually symmetric. So we'll continue with the equilibrium equations in our next class. Thank you. Okay everyone, we'll now be discussing about the equilibrium equations, and we'll first physically understand what it is and then derive the mathematical form of it. So let's sort of go and do that. One of the things which you should know is that when we say it is the equilibrium equation, where is the equilibrium? I mean, is it the equilibrium of the whole solid? The answer is no. I mean, if you look at, for example, this is your solid. You have a particular point over here, and you have the stresses, say sigma ij, at this specific point. And of course, there is an external loading due to which there is deformation, development of internal forces, and from internal forces we come up to this stresses. So when we say we want to develop equilibrium equation, it's about the point. It's about this one point where equilibrium must exist. And equilibrium of both kinds, in the sense force balance, which is the conservation of linear momentum, and the moment balance, which is the conservation of angular momentum. So these are the two things which you should keep in mind, and let's see how that works out. Okay, so we know that the stress is continuously distributed throughout the solid. For example, sigma ij as a function of x, where x is where the origin is somewhere here, and at any point on the solid the stress will be continuously defined. Since in this course we are dealing with static equilibrium, the summation of forces and moments have to be 0. Okay, one of the other things is that if the entire body is in equilibrium, then all constituting parts of it must also be in equilibrium. Okay, so if you divide this into very tiny parts which can be shrunk to a point in specific, all of them must be in equilibrium if the entire body is to be in equilibrium. Okay, so we will partition our body into certain small subdomains and then see how we go about it. So let's do that. Let's have a small part of an arbitrary body. Okay, so the body may be very big, but a small part of it looks like this. Okay, it has a surface S, it has a volume V. The internal forces are F. The tractions which are acting on this are N. Remember, this is a portion of a solid body. The idea is that since the entire body has to be in equilibrium, all portions of it have to be in equilibrium. So we are taking one arbitrary portion, okay, and we'll now apply the equilibrium conditions over it. Okay, so if we want to now apply the conservation of linear momentum, which means that the summation of all the forces, external forces, must be zero. So this can be written as okay, so F, if you recall, is the body force density. And obviously T is the surface force density or traction. Okay, so this is the condition to write the equilibrium. Now if this is for I equal to 1, you will be able to write T1n ds plus F1 dv equal to 0. For I equal to 2, similarly you will have a T2n ds plus, and similarly for I equal to 3, provided obviously Tn is T1 of n I cap plus T2 of n j cap plus T3 of n, or let me use E1, E2, E3, E1 hat, E2 hat and E3 hat. Similarly, the body force density can also be written as F1 E hat plus F2 E hat plus F3 E3 hat. Okay, so this is how the force balance is done, and you can see the diagram over here. The only forces are the body forces and the surface tractions. So both of them have to equate to 0. Now what we do is, I'll just rub this part out, maybe not. What I'll do is I'll substitute Tin by sigma jinj, which we have done in the previous discussion as well. So Tin can be replaced as sigma jinj ds plus fi dv. Okay, this one equation is actually three equations. Okay, I equal to 1 2 3. That's the advantage of writing three in the index form. Otherwise we would be writing all the three equations like in the direction 1, in the direction 2, in the direction 3, or direction x, direction y, direction z. Okay, next we want to use something called the divergence theorem. Okay, let's see what it is mathematically.
It's given in your textbook. It comes from the conversion of surface integral to a volume integral. Okay, so for this particular case, if you have sigma ji nj, okay, that can be written, let's see, sigma ji nj can be written as, sorry, wrong ink, sigma ji comma j plus fi dv equal to 0. How can this be written? So s, and then you have sigma ji nj ds. This can be written as sigma ji comma j dv. I've just used the divergence theorem. You should pause and go and look at the proof of divergence theorem. It is almost certain that you have used or seen the divergence theorem before, perhaps in your undergraduate course in fluid mechanics, but now is the time to revise it. Please revise the divergence theorem and then come back to this. Okay, now since you have arrived at this, and we use the same argument, which is essentially the zero value theorem, even if you don't remember this, you will recall when I say this. So this entire integral is always equal to 0. Okay, and for any arbitrary volume v, this can only happen when the integrand itself is 0. Okay, so sorry, it's not sigma ji, sigma ji comma j. So because the region V is arbitrary, since this is an arbitrary portion of a solid, and hence the integrand has to be 0 because it's continuous, so that will vanish according to this logic. Okay, you can also check the zero value theorem, but even without that, it's the same thing. Now this, if you expand this index, let's do that. We should get sigma, sorry, wrong ink, should get sigma 1i plus, sorry, sigma 1i comma 1 plus sigma 2i comma 2 plus sigma 3i comma 3 plus fi equal to 0. Now we want to write this for special cases, sigma 1 1 comma 1 plus sigma 2 1 comma 2, or let me just write it in the partial differential form, sigma 1 1 to x1 plus sigma to sigma 2 1 to x2 plus dou sigma 3 1 dou x3 plus f1 is equal to 0. To 2. Now for I equal to 3, okay, now we want to write the sigma 1 1 as sigma xx. Okay, so in the XYZ system, these three equations would look like what I'll do is I'll just use the symbol. This is quite confusing for me. I'll just use the symbol. Okay, let me put it tau. Since I'm using sigma x, that's why. There's no confusion of a factor of 2 when it comes to stresses. And this should be xz. Okay, so this, all the elastic stress fields must satisfy these equilibrium equations in order for the static equilibrium to be present, meaning at all points of this solid, okay, at all points of this solid, the sigma ij must satisfy the equilibrium equation. Of course, if the body force is 0, then this term would not be there, and you can just write sigma ji comma j is equal to 0. So that's the so-called force balance part of it, the conservation of linear momentum. However, for the equilibrium to be valid, it must be not just force balance which has to be done, but also moment balance. And that's the next thing which we want to do. So let's move ahead. Just like we had written the force balance, I will now write the moment balance. Before we proceed, we have to first understand what these things are. Okay, so this symbol which you see, it's called the alternating symbol, and it has a certain value. Just come to that. Okay, so the alternating symbol ijk is equal to +1 if ijk is an even permutation of 1, 2, 3, meaning terms like 1, 2, 3, 2, 3, 1, 3, 1, 2. Okay, they are all equal to 1. This is equal to -1 if ijk is an odd permutation of 1, 2, 3. That would mean 3, 2, 1 is equal to 1, 3, 2. Okay, and it's 0 otherwise. Okay, so any other combination will be a 0.
Now let's see how the moments have been written. So first of all, Tn has been written as, let's see. So for we require a r cross f for the moment, right? M is equal to r cross f. So here xj, or so called x, is the moment arm, and f is basically Tn ds. So let me first show how a dot product can be written. So if you have a dot product of A cross B, okay, we can write it in terms of the alternating symbol, and that would be A cross B is equal to E1, E2, E3, A1, A2, A3, B1, B2, B3. This can be written as IJK, AJ, BK, EI. Okay, so let's see whether this is actually true. So A cross B would be E1 hat, A2 B3 minus B2 A3. Then it would be E2 hat, A1 B3 minus B1 A3. Then it would be E3 hat, A1 B2 minus A2 B1. Okay, this is A cross B. Now if you look at this particular term, let's see how that's written. Alternating I, J, K, A, J, B, K, E, I hat. First, let's repeat over I. So it would be epsilon 1 J, K, A, J, B, K, E, 1 hat plus 2 J, K, A, J, B, K, E2 hat plus epsilon 3 JK AJ BK E. So look at each term now. There's a repetition over J and then there's a repetition over K. 1 1 K A 1 B K E1 hat plus 1 2 K A2 B K E1 hat plus 1 3 K A3 BK E1 hat. Look at the next three terms. So okay, I am not doing it now, and you can see the reason why. It will be, so I am only doing this one, so it will be this plus this. So for these two terms I am not doing the same exercise, but you should do it. Okay, now I'll be doing a repetition over K. Oh, I'm sorry, I think I've
I think this is somewhat of a test of patience, hence all students should go through this test of patience, test of focus, whatever else you would want to call it. Okay, so P1, A1, A1, okay, this term is correct. 2, A1 plus A1. Okay, this term is down now. Sorry, I think I was correct. Plus 1, 2, 3, A2, P3, A1 hat. Okay, you do the honors for the other term, but let's see. E11, so only a few of these terms are plus 1. Okay, 1, 2, 3. Can we see a 1, 2, 3? Yes, there's a 1, 2, 3. That's 1. There's a 2, 3, 1. Okay, not a 2, 3, 1. And then there's a 3, 1, 2. Okay, then 1, 3, 2 is minus 1. Okay, that's it. All other terms are 0. Right? So this will only contribute to these two terms, and I'm sure you will be able to do the math for the other two. And this minus sign looks like it will actually cancel out with another similar term with a positive sign, or not. Okay, or not, actually it will be a minus like over here. So this is how you would proceed, and you would get the A cross B as this value. Now if I want to write a moment due to the traction, so the surface force density first has to be converted, let me just call it K, to the force. This is the force 1, and the moment arm is xj, and then this would be ijk. So just see this and you will perhaps see. So aj is xj and bk is this one. So this is entire bk, and of course it will there be a vector sign which I have missed out. Okay, so that's the reason you can write it in this particular form. So in reality this entire thing has a vector sign also, which is ei hat. Okay, but since this entire vector will be 0, that means that individually all of its components are the 0, and hence this is that individual component which is there in front of you. Okay, by a similar logic the body forces would be F K dV, because F is the body force density, and the moment arm would be xj, so Eijk will give you the moment. So that's how you are able to write this equation and say that this is the moment balance or the conservation of angular momentum. Okay, so let me just write that again since I will not be able to see it. Okay, so let me just say this is S. Okay, so this is what we had written, and now we want to again substitute the terms for traction, so let's do that. So Tk will be sigma Lk NL ds. This term is written over here, and
Okay, so this is the same which we have done before, only the symbols change, and the reason for that is we don't want any confusion with the other j's and i's and so on. Okay, now we again want to apply the divergence theorem. So let's see how that can be done. Again, the surface integral has to be converted into the volume integral. The logic is that we want only one type of integral to prevail, so that using the zero value theorem is easy. Okay, so that makes this ijk xj sigma lk. Okay, so then again we want to see this once more, how this is done. So let's go back to the divergence value theorem over here. Let me use a red, not a red ink, say a green ink over here. So we have, what we have is okay, so the way to read this is read this entire thing as 1, okay, with L being the common factor. So you should have, this is surface integral, this will be volume integral dv eijkxj sigma lk comma, what is the last thing, k, so that will be k. Okay, so this is exactly what we have done. The last thing has to be taken a partial, so derivative of xk. Okay, so that's what we have done at this particular step. Now we don't have much to do. I mean, life is not as simple as it was in the earlier case, so we'll have to just expand it and see whether some simplification can be done. So let's see that expansion. This is a differentiation operation, okay, partial differentiation. So we have to use the chain rule of differentiation. So first we differentiate I, j, k, comma, l, keep the other two as they are. Then differentiate x, j, comma, l, keep the other two as they are. Then differentiate the third sigma lk, keep the other two as they are. Okay, and then the last one, sorry, is this one is xjfk dv equal to 0. Okay, so some things are easy. This thing is 0 because epsilon ijk can only be either 0, 1 or minus 1, and if you partially differentiate it with respect to xl, it will only be 0. So that's why this term is 0. This term on the other hand will be dou xj or by dou xl. This will be equal to 1 if j is equal to l, and will be equal to 0 if j is not equal to l. For example, dou x1 by dou x1 will be equal to 0, sorry, it will be equal to 1. Dou x2 by dou x2 will be equal to 1, and dou x3 by dou x3 will be equal to 1. Dou x1 by dou x3 or dou x2 by dou x1 will all be equal to 0. So this is as good as delta JL, and hence this is written as delta JL. Okay, the canonical delta function which is there. Okay, so this is done, and let's write the remainder of these terms. So this implies that the volume integral
ijk delta jl sigma lk plus ijk xj sigma lk comma l plus xj fk. Okay. Now let's write out a few terms. Do you recall this thing? There is a way to simplify this. Okay, that would be writing it as sigma jk. Okay, this particular term can be simplified. Let me just write out in another ink. Okay, we have seen this property before. Then with a proof. Then we want to put this as a minus fk. Remember, sigma ji comma j plus fi is equal to 0. Okay, so replace j with l and I with k. So l k comma l plus fl is equal to 0, and that's where this can be done. So this would be minus epsilon I j k x j f k, and the last term would be I j k x j f k dv equal to 0. This and this would get cancelled, and we would get okay. So we have actually used the equilibrium equation for the force balance over here. Okay, since for equilibrium both of them have to be valid, so you can see how both the angular and the linear momentum are being conserved. So this is what we have until now. Now let's use the same argument as before. Because the volume V is arbitrary and this is always equal to 0, this can only mean that the integrand itself is 0. Okay, so this is where we have until now. Now we have to undertake a small question from our textbook, since it's directly needed. I think it's from chapter 1. So let's do that question. If Aij is a symmetric matrix, a tensor is a matrix, but every matrix is not a tensor, so that should be okay. If Aij is a symmetric matrix and Bij is in any antisymmetric matrix, prove that in general the product Aij Bij is 0. Okay, so let's see how we can do this particular question. Let's see what Aij Bij is. We have to prove that this is equal to 0. So let's write it as Aij should be Aji Bij, okay, because Aij is equal to Aji. It's a symmetric matrix. Now this can be written as minus of 2 times of Aji Bji, because Bij is minus of Bji. It's anti-symmetric. Okay. Now in this product I can interchange, sorry, it's not a 2. I can interchange I and j. I and j can be interchanged. Okay, because they are just dummy indices and they will both give the same value since all of them go from 1 to 3. So you will have the summation of exact same 9 terms as you would have over here. This implies that 2 times of Aij Bij is equal to 0. Now since 2 is not equal to 0, the only possibility is that Aij Bij is equal to 0 and hence proved. Okay, so this has proven that the general product Aij Bij is 0 if one of them is symmetric and the other is anti-symmetric. Okay, so that's the first thing. Now I want to make a claim over here. The claim I want to make is that epsilon ijk is anti-symmetric in jk. First thing, this equation which you see, it's actually not one equation but 3 equations, right? Because j and k obviously will disappear after you expand it, but I will remain. So it's I equal to 1, you will have 1, I equal to 2, you have 2, and so on. The reason is because you were only working with one term when you wrote this equation. I had already told you that this is actually one component of the vector, but since the overall vector was 0, which is the moment, hence the individual components will also 0. Okay, now we have said that Eijk is anti-symmetric in Jk. Can you see that? Is E123 equal to minus E32? Yes, right? 123 is 1, 132 is minus 1. Is E231 equal to minus of E213? Yes, okay. And is E312 minus of 321? Yes, okay. So Eijk is indeed anti-symmetric in Jk, which is the last two indices. Okay. So for I equal to 1, this would be Jk sigma Jk equal to 0. For I equal to 2, it would be Jk sigma Jk equal to 0. And I equal to 3, it would be 3Jk sigma Jk is equal to 0. Now we have just seen if the product Aij Bij is equal to 0 and one of them is symmetric, the other of them is anti-symmetric, you will have this product as 0. Now since you have already found out the product is 0, okay, you have already found out that this product is 0, and since one of them is anti-symmetric in Jk, the other has to be symmetric in Jk. Okay, and this proves that stress is symmetric. Okay, so this is the big conclusion that this is where we were. Since jk is anti therefore sigma jk is symmetric for this product to be 0, just based on what we have done right now. Okay, so this proves that stress is symmetric, and by this logic you already knew tau xy is tau yx and tau yz is equal to tau zy and tau zx equal to tau xz. Okay, remember you had done this perhaps earlier when you were trying to write the stresses, and then you would multiply by forces and then balance the moment about it. You are doing exactly the same thing now. You are balancing the moments, but of course without the geometry. You are doing it in the index notation, and it's much more mathematically convenient in a three-dimensional system. Imagine applying this method which you had done before to a three-dimensional case. It would be very, very cumbersome. So that's one advantage of doing this. Okay, so sigma ij now we can very proudly write is sigma ji. This is one thing which I had already spoken many times before, that stress is symmetric, but I have not yet shown. Well, now I have shown that. Now let's revise the equilibrium equation which we had written after the force balance. That was sigma ji comma j plus fi equal to 0. Then after the moment balance, we have found that sigma ji is equal to sigma ij. Hence this equation can be written as sigma ij comma j plus fi is equal to 0. So this is the equilibrium equation. This is what the stress at any point in a solid must satisfy for the overall body to be in equilibrium. And this combines both the conservation of angular and linear momentum, this equation. Okay, this one only is, this is something which we arrived at using the moment balance, but this equation is combining both of them. So both of these results will be useful in some form of the or the other, but very proudly you can write that this is the equilibrium equation or equations, because for I equal to 1, I equal to 2, I equal to 3, you will have different values. So we'll be using this very often in our discussions, and this also brings us or closes this chapter or discussion on stress. The next topic which we'll be studying is about the linear elasticity or Hooke's law, basically the connection between stress and strain. Now this is a good time to point out to you again, the way we have developed the theory of stress is completely independent of the way we have developed the theory of strain. Okay, they are completely starting off. So one was starting from displacements and coming to strains, the other was starting for forces and coming up to tractions and stress, and then the transformations and principal values and so on for both of them. But the development of the theories is independent of each other. It is only now that we need to connect it, because the materials which we are assuming in this course are linear elastic, so they will follow the so-called Hooke's law, and there will be a connection between the value of stress to the value of strain. So we'll see that in the discussions to follow. Thank you.